The Riemann hypothesis is one of the most famous and long-standing unsolved problems in mathematics. It is deeply connected to the distribution of prime numbers and has far-reaching implications in number theory. The hypothesis concerns the Riemann zeta function, which is a complex function defined for complex numbers. This function, originally studied by Bernhard Riemann in the 19th century, is essential for understanding the density and distribution of prime numbers. The hypothesis asserts that all non-trivial zeros of the Riemann zeta function have a real part equal to 1 divided by 2. In other words, if we express these zeros in the form of a complex number, their real component must always be precisely 1 divided by 2. Understanding why the Riemann hypothesis is so crucial requires an appreciation of prime numbers. Primes are the fundamental building blocks of the number system, and their distribution has fascinated mathematicians for centuries. Although primes appear irregularly along the number line, Riemann's work revealed that their occurrence is linked to the zeros of the zeta function. If the hypothesis is correct, it would confirm and refine many known results in number theory, improving predictions related to the prime number theorem and leading to further advancements in mathematical research. The hypothesis has been extensively tested numerically. Computers have verified that the first several trillion non-trivial zeros of the zeta function lie on the critical line where the real part equals 1 divided by 2. However, numerical evidence alone does not constitute a proof, and a general mathematical verification remains elusive. Despite significant efforts, mathematicians have yet to develop techniques strong enough to resolve this problem definitively. Several attempts to prove or disprove the hypothesis have led to deep insights in various areas of mathematics, including complex analysis, algebraic geometry, and even quantum physics. Some researchers have explored random matrix theory, finding surprising connections between the zeta function's zeros and the eigenvalues of certain random matrices. Others have considered the hypothesis from the perspective of number theory, using advanced techniques such as the Selberg trace formula and L functions. The Riemann hypothesis is one of the 7 Millennium Prize problems, identified by the Clay Mathematics Institute as central challenges in modern mathematics. A proof or counterexample would not only resolve a question that has persisted for over a century, but also significantly impact cryptography, computational mathematics, and physics. Despite its complexity, the problem continues to attract interest from mathematicians and enthusiasts alike. Every year, new approaches emerge, some offering partial results or novel insights. Whether the hypothesis is ultimately proven true or false, its study has already led to the development of powerful mathematical tools and techniques. If resolved, the implications would be profound, reshaping entire areas of pure and applied mathematics. Until then, the Riemann hypothesis remains an enduring mystery, standing as a testament to the depth and challenge of mathematical inquiry. Goldbach's conjecture is one of the oldest unsolved problems in number theory, and it is named after the German mathematician Christian Goldbach, who first proposed it in a letter to Leonhard Euler in 1742. The conjecture states that every even integer greater than 2 can be expressed as the sum of 2 prime numbers. In other words, for every even number greater than 2, there exist 2 prime numbers such that when added together, they equal that even number. To break this down further, a prime number is a number greater than 1 that has no positive divisors other than 1 and itself. The first few prime numbers are 2, 3, 5, 7, 11, and so on. An even integer is any number that is divisible by 2, such as 4, 6, 8, 10, and so on. According to Goldbach's conjecture, any even number greater than 2 should be able to be written as the sum of 2 primes. For example, the number 4 can be written as 2 plus 2, 6 can be written as 3 plus 3, and 8 can be written as 3 plus 5. Despite its simplicity, Goldbach's conjecture has remained unproven for over 280 years. Mathematicians have tested the conjecture for large numbers, and so far, it has held true for every even integer up to 4 times 10 to the 18th, 4 followed by 18 zeros. However, a general proof for all even integers has not yet been found. This leaves the conjecture as a conjecture, meaning it is a statement that is believed to be true but has not been rigorously proven. There are 2 forms of Goldbach's conjecture. The original form is called the strong or binary Goldbach conjecture, which asserts that every even number greater than 2 is the sum of 2 primes. A weaker version of the conjecture is called the odd Goldbach conjecture, which suggests that every odd number greater than 5 can be written as the sum of 3 primes. The strong version has received more attention from mathematicians, and while it has been verified computationally for large numbers, a formal proof remains elusive. Many notable mathematicians have attempted to prove Goldbach's conjecture over the years. Some have made significant progress in related areas, such as proving results that support the conjecture under certain conditions. One of the most important contributions came from the mathematician Ivan Vinogradov in the 1930s. Vinogradov showed that every sufficiently large odd integer can be written as the sum of 3 primes, which provided a partial result for the odd Goldbach conjecture. However, this does not directly prove the strong Goldbach conjecture for all even numbers. Other mathematicians, such as Harold Helfgott, have made progress by using advanced techniques from the field of analytic number theory, such as the circle method. This method, originally developed by the mathematician Godfrey Harold Hardy and John Edensor Littlewood, is used to understand the distribution of prime numbers. Despite these efforts, a complete proof of Goldbach's conjecture has remained out of reach. In conclusion, Goldbach's conjecture is a fundamental question in mathematics that has intrigued mathematicians for centuries. While substantial evidence exists to support the conjecture, a rigorous proof is still lacking. The conjecture continues to be a topic of active research in number theory, with mathematicians hoping to unlock the final piece of this long-standing puzzle. The twin prime conjecture is another famous unsolved problem in number theory that has intrigued mathematicians for centuries. This conjecture asserts that there are infinitely many pairs of prime numbers that differ by exactly 2. These pairs of primes are called twin primes. A prime number is a natural number greater than one that has no positive divisors other than 1 and itself, such as 2, 3, 5, 7, and so on. A twin prime pair consists of 2 prime numbers where the difference between them is exactly 2. For example, 3, 5, 5, 7, and 11, 13 are all twin primes, as the difference between the 2 numbers in each pair is exactly 2. To restate the conjecture more formally, there are infinitely many prime numbers p such that p and p plus 2 are both prime. In other words, for every large number, there are still pairs of prime numbers that are 2 apart. For instance, after 5 and 7, we have 11 and 13, 17 and 19, and so on. The conjecture suggests that no matter how large the numbers get, we can always find more pairs of twin primes. The twin prime conjecture was first proposed by the mathematician Alphonse de Polignac in 1846, but it is often associated with the work of the famous mathematician Christian Goldbach, who made significant contributions to prime number theory. The conjecture, like Goldbach's conjecture, has resisted proof for over 150 years. While mathematicians have proven various results related to the distribution of primes, they have not been able to prove that there are infinitely many twin primes. One of the key challenges in proving the twin prime conjecture is the difficulty in understanding the distribution of prime numbers. Prime numbers, by their very nature, are somewhat irregular. Although they become less frequent as numbers increase, they never entirely disappear. The study of prime numbers is one of the central topics in analytic number theory, which uses advanced mathematical tools to study the behavior of primes and their distribution. Despite these challenges, significant progress has been made in understanding the conjecture. In 2013, the mathematician Yitang Zhang made a groundbreaking result that brought attention to the twin prime conjecture once again. Zhang proved that there are infinitely many pairs of primes that differ by, at most, 70 million. While this result does not directly prove the twin prime conjecture, it represents a significant step forward by showing that there are many pairs of primes with a small gap, and the gap can be reduced further with more work. This was the first major breakthrough in the direction of proving the conjecture in decades and revitalized efforts to tackle the problem. Since Zhang's work, other mathematicians have made further progress, reducing the gap between twin primes from 70 million to smaller numbers. As of now, the gap has been reduced to 246, though this still does not fully prove that the gap can eventually reach 2, as required by the original conjecture. The twin prime conjecture is deeply connected to other unsolved problems in number theory, such as the Goldbach conjecture and the famous Riemann hypothesis. Many of the methods used to study twin primes involve advanced concepts from analytic number theory, such as the distribution of prime numbers and the properties of prime gaps. Twin primes continue to be a central topic of research in mathematics, with mathematicians hoping that new techniques and ideas will eventually lead to a proof of the conjecture. The Collatz Conjecture, also known as the 3x+1 conjecture, is a famous unsolved problem in mathematics that deals with a simple iterative process involving positive integers. Despite its simplicity, it has puzzled mathematicians for decades due to the complexity of its behavior and its resistance to proof. The conjecture was first proposed by the German mathematician Lothar Collatz in 1937 and remains one of the most intriguing unsolved problems in mathematics. The Collatz conjecture is based on an iterative sequence defined as follows. Take any positive integer n. If n is even, divide it by 2. If n is odd, multiply it by 3 and add 1. Then, repeat the process with the resulting number, continuing this sequence indefinitely. The conjecture asserts that no matter which positive integer you start with, the sequence will eventually reach the number 1. Once the sequence reaches 1, it will enter a loop, 1 to 4 to 2 to 1, repeating indefinitely. In other words, the Collatz conjecture suggests that for any positive integer n, after a finite number of steps, the sequence will always reach 1. As shown in this example, the sequence eventually reaches 1 after a finite number of steps. The Collatz conjecture proposes that this behavior is true for all positive integers, although no one has been able to prove it for all numbers. The Collatz conjecture is deceptively simple to understand, but proving it has proven to be exceptionally difficult. The conjecture has been tested for very large numbers using computers, and no counterexample has been found. For all tested integers, the sequence eventually reaches 1, supporting the conjecture. However, despite extensive computational evidence, no general proof has been found to demonstrate that the sequence will always reach 1, regardless of the starting number. The conjecture is often regarded as an example of how simple rules can lead to highly unpredictable and complex behavior. Although the Collatz conjecture is easy to state, its unpredictable nature has made it difficult to solve. One of the challenges is that the behavior of the sequence is highly irregular. While some starting numbers quickly reach 1, others can take much longer and undergo seemingly erratic jumps between large and small numbers. The irregularity of the sequence makes it difficult to apply standard mathematical techniques to prove the conjecture. Over the years, many mathematicians have attempted to prove or disprove the Collatz conjecture, but so far, no one has been successful. Several approaches have been proposed, including using advanced concepts from number theory, algebra, and dynamical systems, but none of these have led to a conclusive proof. Some researchers have suggested that the problem may require entirely new mathematical techniques that have yet to be discovered. One interesting feature of the Collatz conjecture is its connection to other mathematical areas, such as prime numbers and the distribution of powers of 2. Some mathematicians have explored the conjecture in the context of random processes, trying to model the sequence as a random walk, or using probabilistic methods to understand its behavior. However, despite these efforts, the Collatz conjecture remains an open problem in mathematics. In conclusion, the Collatz conjecture is a deceptively simple yet profoundly complex problem that has remained unsolved for more than 80 years. While the conjecture has been verified for large numbers using computers, a general proof that applies to all positive integers has yet to be found. The conjecture continues to challenge mathematicians and offers a fascinating example of how simple rules can lead to complex and unpredictable behavior. As such, it remains a central question in mathematics, drawing the interest of both amateur and professional mathematicians alike. The Birch and Swinnerton-Dyer conjecture is a central unsolved problem in the field of number theory and algebraic geometry, specifically dealing with elliptic curves. Named after mathematicians Brian Birch and Peter Swinnerton-Dyer, who first proposed the conjecture in 1963, it remains one of the 7 Millennium Prize problems, for which the Clay Mathematics Institute has offered a prize of $1 million for a correct solution. Elliptic curves are equations of the form y squared equals x cubed plus x plus b, where a and b are constants. These curves are fundamental objects in mathematics, with applications in number theory, cryptography, and many areas of algebraic geometry. The Birch and Swinnerton-Dyer conjecture is concerned with the number of rational points, which are points on the elliptic curve whose coordinates are both rational numbers. More specifically, the conjecture connects the rank of an elliptic curve to the behavior of its L function at s equals 1. The rank of an elliptic curve is an integer that describes the number of independent rational points of infinite order on the curve. In other words, the rank measures how many different rational points exist that are not just multiples of each other. The L function of an elliptic curve is a complex function that encodes information about the number of rational points on the curve and other arithmetic properties. The Birch and Swinnerton-Dyer conjecture proposes that there is a deep relationship between two things. 1. The rank of an elliptic curve, which measures the number of independent rational points of infinite order. 2. The behavior of the L function of the elliptic curve at s equals 1. The conjecture states that the rank of an elliptic curve is related to the value of its L function at s equals 1. Specifically, it suggests that if the L function of the elliptic curve does not vanish at s equals 1, i.e., it is non-zero, then the rank of the curve is 0. If the L function does vanish at s equals 1, i.e., it is 0, then the rank of the curve is greater than 0. In other words, the conjecture provides a way to determine the rank of an elliptic curve by examining the behavior of its associated L function. The L function, in turn, encodes information about the curve's rational points. If the conjecture is proven true, it would give mathematicians a powerful tool for understanding the structure of elliptic curves and their rational points. One of the key features of the conjecture is its remarkable connection between algebraic geometry and analytic number theory. The study of elliptic curves and their rational points has deep connections to both fields, and the Birch and Swinnerton-Dyer conjecture serves as a bridge between them. It also has important implications for other areas of mathematics, such as Diophantine equations, which involve finding integer or rational solutions to polynomial equations. Despite extensive computational evidence supporting the conjecture, a general proof has not yet been found. Researchers have verified the conjecture for many specific cases, and it has been shown to hold true for elliptic curves of low rank. However, a general proof that applies to all elliptic curves remains elusive. One of the challenges is that the conjecture involves both analytic and algebraic aspects of elliptic curves, making it difficult to apply standard mathematical techniques. In recent years, there has been some progress in understanding the Birch and Swinnerton-Dyer conjecture. For example, mathematicians have made significant advances in understanding the properties of L functions, and new tools have been developed to study the rank of elliptic curves. However, despite these advances, a complete proof of the conjecture is still unknown. Beal's conjecture is an unsolved problem in number theory, proposed by American mathematician Andrew Beal in 1993. The conjecture is a generalization of Fermat's last theorem and deals with the solutions to certain Diophantine equations. A Diophantine equation is an equation where only integer solutions are sought. Specifically, Beal's conjecture deals with equations of the form x raised to the power of a plus y raised to the power of b equals z raised to the power of c, where x, y, and z are positive integers, and a, b, and c are integers greater than 2. The conjecture suggests that the equation above does not have any solutions where all three of x, y, and z are coprime, i.e., their greatest common divisor is 1, unless a, b, and c share a common prime factor. To break this down, in the equation, x raised to the power of a plus y raised to the power of b equals z raised to the power of c, x, y, and z represent positive integers, while a, b, and c represent exponents. Beal's conjecture asserts that if x, y, and z are coprime, meaning they have no common factors other than 1, then there are no integer solutions for x, y, and z unless a, b, and c have a common prime factor. This conjecture can be seen as a generalization of Fermat's last theorem, which states that there are no integer solutions to the equation. N raised to the power of n plus y raised to the power of n equals z raised to the power of n for any integer value of n greater than 2. Fermat's last theorem was proven by Andrew Wiles in 1994. But Beal's conjecture extends this idea by considering equations with different exponents, a, b, and c, and allowing the exponents to be different values. Beal's conjecture suggests that when a, b, and c are greater than 2, the only solutions to ex raised to the power of a plus y raised to the power of b equals z raised to the power of c are those where a, b, and c share a common prime factor. This additional condition, that a, b, and c must share a common prime factor, is what distinguishes Beal's conjecture from Fermat's last theorem, and it presents a more complex and broad extension of Fermat's idea. For example, suppose we have the equation x raised to the power of 3 plus y raised to the power of 4 equals z raised to the power of 5. According to Beal's conjecture, there would be no integer solutions to this equation unless the exponents 3, 4, and 5 share a common prime factor. In cases where they do not, no integer solutions should exist. Since its formulation, Beal's conjecture has attracted a great deal of interest from number theorists. The conjecture is a part of the broader study of Diophantine equations, which aim to understand when equations with integer solutions exist. Diophantine equations are named after the ancient Greek mathematician Diophantus, who studied such equations. These kinds of equations are notoriously difficult to solve and have led to the development of many advanced techniques in algebraic number theory and other areas of mathematics. One of the fascinating aspects of Beal's conjecture is that it has not yet been proven or disproven. despite its similarity to Fermat's last theorem, which was famously proved after centuries of attempts. In 1997, Beal offered a monetary reward of $1 million for anyone who could either prove or disprove the conjecture, making it one of the most sought-after problems in mathematics. The conjecture's appeal lies not only in its similarity to Fermat's last theorem, but also in its broader implications. If proven true, Beal's conjecture would help mathematicians understand more about the structure of Diophantine equations and the relationships between integers and their exponents. It would also offer insight into the conditions under which certain types of equations can have integer solutions. On the other hand, if the conjecture were disproven, it would likely lead to the discovery of new techniques for solving Diophantine equations. Despite efforts to find a proof or counterexample, Beal's conjecture remains open. Some progress has been made in understanding the structure of equations of the form x raised to the power of a plus y raised to the power of b equals z raised to the power of c. And mathematicians have studied cases where the exponents are specific values. However, no general proof or disproof has been found. The P versus NP problem is one of the most fundamental and unsolved questions in computer science and mathematics. It was formally proposed by Stephen Cook in 1971 and has since become a central problem in the theory of computation. The question revolves around the complexity of certain computational problems and whether problems that can be verified quickly can also be solved quickly. In essence, the P versus NP problem asks whether every problem whose solution can be quickly verified in polynomial time can also be quickly solved, also in polynomial time. P stands for polynomial time. It is a class of problems that can be solved in a time that is a polynomial function of the size of the input. More formally, a problem is in P if there exists an algorithm that can solve the problem in O of n to the power of k time for some constant k, where n is the size of the input. NP stands for non-deterministic polynomial time. This class of problems involves decision problems for which a proposed solution can be verified in polynomial time. In other words, if someone gives you a potential solution, you can check if it's correct relatively quickly, in polynomial time. However, finding that solution from scratch may take much longer. A key aspect of NP problems is that, although we don't necessarily know how to solve them quickly, we can verify solutions quickly once they are provided. To put it simply, a problem is in P if it can be both solved and verified quickly. A problem is in NP if, even though finding a solution might be hard, verifying a given solution is easy in polynomial time. The P versus NP problem asks whether these two classes are the same. In other words, is it true that every problem that can be verified quickly, i.e. in NP, can also be solved quickly, i.e. in P? This question remains unresolved and is one of the 7 Millennium Prize problems for which the Clay Mathematics Institute has offered a $1 million prize for a correct solution. The conjecture posed by the P versus NP problem can be summarized as follows. Is P equal to NP? This means that, if a problem can be verified quickly, in polynomial time, can it also be solved quickly in polynomial time? More formally, does P equal NP? The P versus NP problem has far-reaching implications in various fields, particularly in computer science, cryptography, operations research, artificial intelligence, and more. Here are some key points about the importance of this question. Many cryptographic systems, including widely used methods like RSA encryption, relies on the assumption that certain problems are difficult to solve, in NP, but easy to verify. If P equals NP, it would imply that these problems could also be solved efficiently, potentially breaking the security of these systems. In fields such as operations research and artificial intelligence, Many real-world problems are framed as optimization problems. If P equals NP, it would mean that many of these difficult problems could be solved quickly, potentially revolutionizing industries such as logistics, finance, and even machine learning. The question of whether P equals NP lies at the heart of computational complexity theory, which studies the inherent difficulty of computational problems. A solution to the P versus NP problem would clarify the limits of what can be computed efficiently and help classify problems in terms of their difficulty. Many problems in AI, such as proving the correctness of programs, pattern recognition, and even game-playing strategies, are examples of NP-complete problems. These problems are considered to be at the most difficult end of NP problems. If P equals NP, many AI systems could potentially solve such problems more effectively. One important concept in the P versus NP debate is the class of problems known as NP-complete. These are problems in NP that are, in a sense, the hardest problems in NP. If any NP-complete problem can be solved in polynomial time, i.e., is in P, then every problem in NP can also be solved in polynomial time, meaning that P equals NP. Despite extensive research, the question of whether P equals NP remains unanswered. There is strong belief among many computer scientists that P is not equal to NP, meaning that there exist problems in NP that cannot be solved quickly in polynomial time. This belief stems from the fact that no one has been able to find efficient algorithms for NP-complete problems, and most experts believe that such algorithms do not exist. However, this belief is not a proof, and proving that P is not equal to NP is a monumental task. On the other hand, proving that P equals NP would revolutionize our understanding of computation and problem solving. If it were shown that P equals NP, it would mean that many problems thought to be intractable could actually be solved efficiently. This would have profound consequences across many domains, from cryptography to optimization to artificial intelligence. The Navier-Stokes existence and smoothness problem is one of the most important unsolved questions in the field of mathematical fluid dynamics. It is concerned with the behavior of solutions to the Navier-Stokes equations, which describe the motion of incompressible fluids. The equations are used to model a wide range of phenomena, from the flow of air around an airplane to the movement of water in the ocean. Despite their practical applications, the fundamental question of whether solutions to the Navier-Stokes equations exist and are smooth, i.e., free of singularities, remains unresolved. The Navier-Stokes equations are a system of partial differential equations that describe the motion of a viscous, incompressible fluid. They are derived from the conservation of mass, momentum, and energy, and they form the foundation of fluid mechanics. These equations are fundamental in understanding the behavior of fluid flows in various settings. They are a system of nonlinear equations that describe how the velocity of a fluid changes over time and space. However, despite their wide applicability, there are still many unanswered questions regarding the existence and smoothness of solutions to these equations. The Navier-Stokes existence and smoothness problem asks whether smooth, i.e., continuously differentiable solutions to the Navier-Stokes equations exist in three-dimensional space for all times. In simpler terms, it asks whether, given initial conditions for the velocity field of a fluid, we can guarantee that the fluid's motion will always have smooth and well-behaved solutions without any singularities, like a sudden infinite velocity or pressure at some point. The problem can be broken down into two parts. Existence. Does a smooth solution exist for all time given certain initial conditions? Smoothness. Are the solutions to the equations smooth, differentiable, for all times, or do they develop singularities, i.e., points where the solution becomes infinite or undefined? The question is critical because if it could be proven that solutions always exist and are smooth, it would greatly improve our understanding of fluid dynamics. On the other hand, proving that solutions can develop singularities would indicate that the equations do not always predict physically realistic behavior. The Navier-Stokes existence and smoothness problem is one of the 7 Millennium Prize problems established by the Clay Mathematics Institute in 2000. If someone proves or disproves this problem, they will be awarded a prize of $1 million. The problem remains unsolved, despite decades of research by mathematicians and physicists. The importance of this problem extends beyond mathematics and physics. It has direct implications for many fields, including engineering, meteorology, oceanography, and aerodynamics. For example, the accurate modeling of air and water flow is crucial in designing airplanes, predicting weather patterns, and understanding the behavior of oceans and rivers. If singularities were found to exist in fluid flow, it could change how engineers approach the design of systems involving fluid dynamics, such as pipelines, aircraft, and engines. One of the challenges in solving the Navier-Stokes existence and smoothness problem is the highly nonlinear nature of the equations. Nonlinear equations are notoriously difficult to solve because small changes in the input can lead to large, unpredictable changes in the output. This makes finding an analytical solution to the Navier-Stokes equations, or proving the existence and smoothness of solutions, extremely challenging. The case of two-dimensional fluids is much more understood, and solutions to the Navier-Stokes equations in 2 dimensions are known to exist and remain smooth. However, in 3 dimensions, the equations become significantly more complicated, and the behavior of solutions is much harder to predict. In 3 dimensions, solutions to the equations may develop singularities, which would lead to infinite velocities or pressures at certain points. Whether such singularities can develop under realistic physical conditions is still an open question. If the Navier-Stokes existence and smoothness problem were solved, it would have profound implications for our understanding of fluid dynamics. A proof of existence and smoothness would guarantee that fluid flows behave in a regular, predictable manner. On the other hand, a proof that solutions can develop singularities would deepen our understanding of turbulence and other phenomena that arise in fluid dynamics. Despite significant progress in related fields, including turbulence theory and the study of partial differential equations, a full solution to the problem remains elusive. Researchers have made strides in proving the existence of solutions under certain conditions, but the question of whether these solutions are smooth and free of singularities remains unresolved. In conclusion, the Navier-Stokes existence and smoothness problem is one of the most important unsolved questions in mathematics and physics. It is a fundamental question in the field of fluid dynamics, with wide-ranging implications for many scientific and engineering disciplines. Solving this problem would provide crucial insights into the behavior of fluids and help to improve our understanding of the natural world. Until a solution is found, the problem will continue to challenge mathematicians and physicists alike. The Hodge Conjecture is one of the 7 Millennium Prize problems, and is a major unsolved problem in the field of algebraic geometry. Proposed by the British mathematician W.V.D. Hodge in 1950, it is a conjecture about the relationship between the topology of a complex algebraic variety and the geometry of its algebraic cycles. The conjecture is particularly significant in the study of complex manifolds and has profound implications in both mathematics and theoretical physics. The Hodge Conjecture deals with the study of algebraic cycles, which are certain subvarieties of a complex algebraic variety that are defined by algebraic equations. The conjecture is concerned with understanding how the topology, i.e., the topological structure, of a variety relates to the structure of its algebraic cycles. In mathematical terms, the Hodge conjecture asserts that certain classes of cohomology classes on a smooth projective algebraic variety can be represented by algebraic cycles. To explain this more simply, the conjecture suggests that certain topological features of a variety, specifically cohomology classes, should have a corresponding geometric description in terms of algebraic cycles. This would imply that the algebraic cycles, which are defined by polynomial equations, can be used to describe the topological structure of the variety. The conjecture applies to complex algebraic varieties, which are varieties defined by polynomial equations over the complex numbers. The cohomology of such varieties refers to a collection of algebraic objects that capture information about the variety's shape and structure, such as the number of holes or the way the variety is connected. The conjecture essentially posits that some of these cohomology classes can be represented by algebraic cycles, that is, by geometric objects that can be described by polynomial equations. To give an example, consider a variety that represents the solution set of a system of polynomial equations in several complex variables. The Hodge conjecture suggests that certain topological features of this variety, such as the existence of certain kinds of cycles, can be described by actual solutions to polynomial equations, that is, by algebraic objects. The Hodge conjecture is a generalization of the Hodge theory developed by W.V.D. Hodge in the 1930s. Hodge theory investigates the decomposition of the cohomology of a complex algebraic variety into parts that correspond to geometric objects called Hodge classes. These Hodge classes are cohomology classes that have a specific structure and can be used to describe the variety's geometry in a very precise way. The conjecture asks whether all cohomology classes that are Hodge classes can be realized by algebraic cycles. The conjecture is a statement about the algebraic geometry of varieties, which is the study of geometric objects that can be defined by polynomial equations. In this context, algebraic cycles are higher-dimensional analogues of curves, surfaces, and other geometric objects that can be defined by algebraic equations. The conjecture suggests that certain topological features of algebraic varieties, which can be detected through cohomology, should have a corresponding geometric interpretation in terms of algebraic cycles. One of the key elements of the conjecture is its connection to the concept of projective varieties. A projective variety is a variety that can be embedded in a projective space, which is a space that generalizes the notion of points, lines, and higher-dimensional geometric objects. The conjecture suggests that algebraic cycles on these varieties can be used to describe their topological structure in a very precise way. The Hodge conjecture is part of a broader effort to understand the relationship between the geometry and topology of algebraic varieties. The problem is deep and complex because it involves intricate interactions between algebraic geometry, topology, and number theory. The conjecture has been studied for many years, and while it has been proven for certain special cases, a general proof remains elusive. The significance of the Hodge conjecture goes beyond algebraic geometry. It has connections to various areas of mathematics, including number theory, topology, and mathematical physics. In particular, it has implications for the study of mirror symmetry and string theory in physics, where the geometry of complex varieties plays a crucial role in understanding the structure of the universe at the microscopic level. The Ernst-Strauss conjecture, also known as the Illumination problem, is a well-known unsolved problem in the field of geometry and combinatorics. It was proposed by the German-American mathematician Ernst Strauss in 1948 and has since become a central question in the study of geometric illumination. The conjecture is concerned with the problem of how to illuminate a polygonal room with straight walls using a fixed number of light sources. Specifically, it asks whether it is possible to illuminate every point inside a simple polygon with a finite number of light sources placed on the boundary of the polygon. The conjecture has been of interest to mathematicians, especially in the context of computational geometry, as it touches on both geometric covering and optimization problems. In more formal terms, the Ernst-Strauss conjecture suggests that any simple polygon in a two-dimensional plane can be fully illuminated by placing light sources on the polygon's boundary. The challenge is to determine the minimum number of light sources required for this illumination. A light source is assumed to emit light in all directions along the line of sight, and the goal is to ensure that every point within the polygon can receive light from at least one of the sources. The conjecture asserts that this can always be achieved with a fixed number of light sources, depending on the shape of the polygon. The illumination problem involves the concept of visibility. A point inside the polygon is considered illuminated if there is a direct line of sight from a light source on the boundary of the polygon to that point. The visibility graph of a polygon is a graph where the vertices are the boundary points of the polygon, and an edge exists between two vertices if there is a direct line of sight between them. The conjecture suggests that a small number of points on the boundary are sufficient to connect every point inside the polygon to one of these points via a direct line of sight. The basic version of the conjecture applies to simple polygons, which are polygons that do not self-intersect. The more general form of the conjecture applies to more complex polygons, including those with holes or concave shapes. In this case, the goal is still to determine the number of light sources required to illuminate the entire area, but the problem becomes more complicated due to the presence of obstacles or indentations in the polygon. One of the key aspects of the illumination problem is determining the minimum number of light sources needed. While it is known that a single light source may not always be sufficient to illuminate every point inside a polygon, the conjecture suggests that a limited number of light sources, possibly as few as 2 or 3, can illuminate any polygonal shape. However, the exact number of light sources required for a general polygon remains unknown. The conjecture has significant connections to other areas of mathematics, such as combinatorial geometry, graph theory, and optimization. The illumination problem is closely related to the concept of guards in art galleries, which involves placing a minimum number of guards in a polygon to ensure that every point inside the polygon is visible to at least one guard. This concept, known as the art gallery theorem, was proven by Victor Klee in 1973, and the strategy for placing guards in a polygon is similar to the problem of placing light sources for illumination. The main difference is that in the art gallery problem, the guards are stationary and only have visual access to the interior, while light sources can illuminate an entire area in all directions. Though the conjecture has been studied for decades, it remains unsolved. Much of the work done on the illumination problem focuses on specific types of polygons, such as rectilinear polygons, where the edges are either horizontal or vertical. In such cases, it has been proven that the polygon can be illuminated with a finite number of light sources, but the general case for arbitrary polygons is still open. One of the challenges in solving the Ernst-Strauss conjecture is the sheer diversity of possible polygonal shapes. For each polygon, determining the optimal placement of light sources to achieve full illumination can be a complex task. Moreover, finding a general method for proving the existence of an optimal solution for all polygons is difficult, given the varying number of sides, angles, and other features that can exist in a polygon. Hadwiger's conjecture is a famous unsolved problem in the field of graph theory, first proposed by the Swiss mathematician Hugo Hadwiger in 1943. The conjecture is a deep and fundamental statement about the connection between graph coloring and minor theory in graphs. It has been central to the study of graph theory for decades and remains one of the most important unsolved problems in the field. the conjecture is concerned with the concept of graph minors and chromatic number. A graph minor is a graph that can be obtained from another graph by deleting edges or vertices and by contracting edges. The chromatic number of a graph is the smallest number of colors needed to color the vertices of the graph such that no two adjacent vertices share the same color. In simple terms, Hadwiger's conjecture states that if a graph G has no kk, complete graph on k vertices, as a minor, then the chromatic number of G is at most k. Here, a complete graph is a graph in which every pair of distinct vertices is connected by an edge. For example, a K4 is a complete graph on 4 vertices, where every pair of vertices is connected by an edge. More formally, Hadwiger's conjecture asserts the following. If a graph G does not contain a complete graph KK as a minor, then the chromatic number of G is at most k. This conjecture suggests that the chromatic number of a graph is related to the structure of the graph's minors, specifically the largest complete graph that can be found as a minor within the graph. For example, if a graph does not contain K4 as a minor, then according to Hadwiger's conjecture, its chromatic number should be at most 3. In other words, the graph can be colored using at most 3 colors without violating the coloring condition. Hadwiger's conjecture is an extension of the 4-color theorem, which states that every planar graph can be colored with at most 4 colors. The 4-color theorem was proven in 1976 by Kenneth Pell and Wolfgang Haken, using a computer-assisted proof. Hadwiger's conjecture generalizes this result by suggesting that the number of colors required to color a graph is tied to the presence of complete graph minors, not just planarity. The connection between graph minors and chromatic numbers is central to the conjecture. The study of graph minors was largely influenced by Robert Tarjan and Neil Robertson, who developed deep results in this area. They introduced the concept of tree width and proved many important theorems about graphs and their minors. The Robertson-Seymour theorem, which provides a characterization of the minors of graphs, is particularly relevant to the study of Hadwiger's conjecture. Hadwiger's conjecture has been proven in several cases. For example, it has been proven for K5, the complete graph on 5 vertices, and for some smaller values of K. In particular, it has been shown that the conjecture holds for graphs that exclude a specific complete graph as a minor, such as K6 or K7. However, the general case remains open, and proving the conjecture for all values of K is a significant challenge. One of the challenges in proving Hadwiger's conjecture is the difficulty in dealing with the vast number of possible graph minors that could appear in a graph. The presence of a minor in a graph does not always provide an immediate or easy way to determine its chromatic number. Furthermore, the relationship between graph minors and chromatic numbers is highly complex and depends on intricate structural properties of the graph. Hadwiger's conjecture has connections to other areas of mathematics, including topology, combinatorics, and mathematical logic. In particular, the theory of graph minors is closely related to the study of planarity and graph embeddings. Additionally, the conjecture has applications in computer science, especially in the areas of graph algorithms, network design, and optimization. Understanding the relationship between graph coloring and graph minors has important implications for solving real-world problems in these fields. Despite much progress, the Hadwiger conjecture remains unsolved. Researchers have made significant contributions by proving special cases and exploring its implications for various types of graphs. However, a complete proof that applies to all graphs remains elusive. In conclusion, Hadwiger's conjecture is a central problem in graph theory that relates the chromatic number of a graph to the minors that it contains. The conjecture suggests that the chromatic number of a graph is bounded by the largest complete graph minor that the graph can contain. While the conjecture has been proven in some cases, the general proof remains an open problem in mathematics, and it continues to inspire research in graph theory, combinatorics, and related fields. The Erdős discrepancy problem is an unsolved problem in the field of number theory and combinatorics, first posed by the Hungarian mathematician Paul Erdős in 1932. The problem involves finding a discrepancy in sequences of integers and has intrigued mathematicians for decades due to its deep connections to various areas of mathematics, including additive combinatorics and sieve theory. The problem is based on the concept of a sequence of integers, specifically a sequence that consists of two values, usually denoted as 1 and -1. The discrepancy of a sequence is defined as the difference between the number of occurrences of 1 and the number of occurrences of -1 up to any given point in the sequence. The Erdős discrepancy problem is concerned with determining how large this discrepancy can get for any given sequence. More formally, the Erdős discrepancy problem can be described as follows. Given a sequence of 1s and -1s, the discrepancy at position n is the sum of the first n terms in the sequence. The goal is to determine whether, for any sequence of 1s and -1s, there exists a subsequence whose discrepancy grows without bound as the sequence progresses. In simple terms, Erdős posed the question: for a sequence of 1s and -1s, is it possible for the discrepancy to grow arbitrarily large, or is there always some bound on how large the discrepancy can get? The discrepancy of a sequence is an important concept because it captures how unbalanced the sequence is between the two values, 1 and -1. A sequence with low discrepancy means that the number of 1s and -1s are roughly balanced as the sequence progresses, while a sequence with high discrepancy means that the number of occurrences of 1 and -1 are highly imbalanced at some point in the sequence. Erdős's original question was whether there exists a sequence of 1s and -1s in which the discrepancy can grow arbitrarily large. He conjectured that such a sequence indeed exists, and that the discrepancy could grow without bound, even for a sequence of finite length. This idea suggests that there is no universal bound on the discrepancy, and that for any sequence, no matter how long, the discrepancy can always be increased by choosing the appropriate sequence of 1s and -1s. The Erdős discrepancy problem has been studied in a variety of ways. In particular, it is connected to the concept of sums of partial sums of sequences, which is a topic in additive combinatorics. Researchers have explored whether there are patterns or structures within sequences of 1s and -1s that would allow for a bound on the discrepancy. The problem is closely related to the Simonetti theorem, a result in combinatorics that provides an answer to a certain class of questions about arithmetic progressions and sequences. Over the years, significant progress has been made toward understanding the Erdős discrepancy problem, particularly in terms of lower bounds for the discrepancy of specific sequences. For example, in 2008, the mathematician Tau and Ziegler proved that, for certain types of sequences, the discrepancy can indeed grow without bound, confirming Erdős's original conjecture for some cases. Their work showed that there exists a sequence of 1s and -1s whose discrepancy grows faster than any fixed bound, although they did not provide a general solution to the problem. Despite these advances, the general case of the Erdős discrepancy problem remains unresolved. While lower bounds for specific sequences have been found, the precise growth rate of the discrepancy for arbitrary sequences is still unknown. Specifically, it remains unclear whether the discrepancy always grows without bound, or whether certain sequences may have a built-in upper limit to their discrepancy. The Erdős discrepancy problem has wide implications for various fields, including additive number theory, combinatorics, and mathematical logic. It is related to questions about the structure of sequences, the distribution of numbers, and the behavior of sums over large sets. The problem also ties into other famous problems in mathematics, such as the Goldbach conjecture and Ramsey theory, which are concerned with similar combinatorial and additive structures. In conclusion, the Erdős discrepancy problem is a fascinating and challenging question in number theory and combinatorics. The problem asks whether there exists a sequence of ones and negative ones whose discrepancy grows without bound, and although progress has been made, a general solution remains elusive. The problem has deep connections to several areas of mathematics and continues to inspire research in additive combinatorics and beyond. The Euler's sum of powers conjecture is a famous conjecture in number theory, proposed by the Swiss mathematician Leonhard Euler in 1770. This conjecture is related to the sums of integer powers and has been a central question in the study of Diophantine equations, which involve finding integer solutions to equations. The conjecture presents a fascinating relationship between powers of integers and sums of other powers, specifically focusing on powers of integers raised to an exponent greater than 2. Euler's sum of powers conjecture suggests that there are no 4 positive integers that satisfy the equation: a raised to the power of n plus b, raised to the power of n plus c, raised to the power of n equals a dot raised to the power of n for n greater than 2, where a, b, c, and d are positive integers. In other words, Euler conjectured that it is impossible to find 4 different positive integers whose nth powers, where n is greater than 2, add up to another integer raised to the same power. The conjecture can be seen as a generalization of Fermat's last theorem, which states that there are no 3 positive integers x, y, and z that satisfy the equation: x raised to the power of n plus y raised to the power of n equals z raised to the power of n for n greater than 2. Fermat's last theorem was proven by Andrew Wiles in 1994. While Fermat's last theorem dealt with the case of 3 integers, Euler's conjecture extends this idea to 4 integers, suggesting that there is no solution to the equation involving 4 integers raised to the same power greater than 2. Euler's conjecture was tested for many values of n, and computational searches did not find any counterexamples for several centuries. For small values of n, no such solutions were found. However, in 1966 a counterexample was discovered for n equals 4. Specifically, it was shown that 27 raised to the power of 4 plus 84, raised to the power of 4 plus 110, raised to the power of 4 equals 144, raised to the power of 4. This discovery refuted Euler's conjecture for n equals 4, proving that a solution exists for 4 positive integers where their 4th powers add up to another 4th power. This counterexample demonstrated that the conjecture was incorrect for this case, and as a result, Euler's sum of powers conjecture was proven false for this case. Despite this counterexample for n equals 4, the conjecture is still believed to hold for higher powers. The conjecture was proven for n equals 3, meaning that there are no 4 positive integers whose cubes sum to another cube. Euler's conjecture, therefore, remains an interesting point of study in the history of number theory and the study of Diophantine equations. The failure of Euler's conjecture for n equals 4 led to the investigation of similar Diophantine problems, and mathematicians have continued to search for other generalizations and counterexamples. While Euler's conjecture has been refuted in certain cases, it remains an important milestone in the history of mathematics, as it led to a deeper understanding of sums of powers and the behavior of Diophantine equations in higher powers. Euler's sum of powers conjecture is part of the broader exploration of sum of powers problems, which continue to be an active area of research. It is closely related to other questions in number theory such as Waring's problem, which involves expressing natural numbers as sums of powers, and the Hardy-Weinberg principle in algebraic number theory, which looks at the solutions to equations involving powers of integers. In conclusion, Euler's sum of powers conjecture was an influential conjecture in number theory, proposed by Euler that dealt with the sum of powers of integers. While it was proven false for n equals 4 after a counterexample was found, it remained significant in the study of Diophantine equations. The failure of the conjecture for n equals 4 has not diminished its importance, as it helped pave the way for future explorations in number theory, especially in the context of sums of powers and the search for solutions to higher-degree Diophantine equations. Pell's equation is a famous Diophantine equation, named after the English mathematician John Pell. Although Pell did not actually solve the equation has been a subject of study for centuries and remains an important part of number theory. Pell's equation is a specific type of quadratic Diophantine equation, which involves finding integer solutions to equations of the form x squared dy squared 1. In this equation, x and y are unknown integers, and d is a given positive non-square integer. The goal is to find integer solutions for x and y that satisfy the equation. Pell's equation is a remarkable problem because it has been extensively studied and solved using various mathematical techniques. The equation is particularly interesting because it involves the difference of two squares and has deep connections to continued fractions, quadratic forms, and the theory of units in number fields. The equation is called Pell's equation because it was studied extensively by John Pell in the 17th century, although it was actually first studied by Brahmagupta, an Indian mathematician, in the 7th century. Brahmagupta provided a method for finding solutions to this equation, and his work laid the foundation for later developments in number theory. One of the key features of Pell's equation is that, for many values of d, the equation has an infinite number of integer solutions. This is because the equation is closely related to the fundamental solution of the equation, which is the smallest solution in positive integers. Once the fundamental solution is found, it can be used to generate all other solutions. This generation process relies on the properties of the equation's solutions and involves the continued fraction expansion of the square root of d. In general, the method for solving Pell's equation involves finding the continued fraction expansion of the square root of d. The continued fraction provides an approximation of the square root of d, and it leads to a sequence of approximations that can be used to find solutions to Pell's equation. The fundamental solution is often the first non-trivial solution in this sequence, and it can be used to generate all other solutions. An important feature of Pell's equation is that it has non-trivial solutions for most values of d. In fact, Pell's equation has a solution if and only if d is not a perfect square, meaning that the square root of d is not an integer. For perfect squares, the equation has no solutions. This is because the equation requires that the difference between the squares of x and y be equal to 1, and this is not possible for perfect squares. The solutions to Pell's equation are often expressed in terms of powers of the fundamental solution. Once the fundamental solution is found, it can be raised to successive powers to generate new solutions. This process exploits the structure of the equation and its relationship to the theory of units in quadratic fields. Pell's equation has many applications in number theory and related fields. It is used to study quadratic fields, algorithms for finding integer solutions to Diophantine equations, and cryptography, among other areas. The methods developed for solving Pell's equation have been applied to other types of Diophantine equations and have helped develop algorithms for solving problems in computational number theory. Pell's equation is also important in the context of algebraic number theory, as it is closely related to the theory of rings of integers in quadratic number fields. The solutions to Pell's equation correspond to the units in these rings, and the equation provides a way to study the properties of these units and their behavior. Despite its long history, Pell's equation continues to be an area of active research. New methods for solving the equation, particularly for large values of d, are continually being developed. Pell's equation also serves as a model for other types of Diophantine equations, and has led to the development of new techniques and algorithms in the field of number theory. In conclusion, Pell's equation is a deep and important problem in number theory that involves finding integer solutions to a specific type of quadratic Diophantine equation. The equation has a rich history, with contributions from mathematicians such as Brahmagupta, Euler, and others. The solutions to Pell's equation are connected to continued fractions and quadratic fields, and they have applications in many areas of mathematics, including algebraic number theory and cryptography. Although the equation has been studied for centuries, it continues to be an important topic in modern mathematical research. Fermat's last theorem is one of the most famous and significant results in the history of mathematics. It was first conjectured by the French mathematician Pierre de Fermat in 1637, and remained unsolved for over 300 years. The theorem deals with the equation x raised to the power of n plus y raised to the power of n equals z raised to the power of n where x, y, and z are positive integers, and n is an integer greater than 2. Fermat's last theorem asserts that this equation has no solutions in positive integers for any value of n greater than 2. Fermat famously wrote in the margin of his copy of an ancient Greek text that he had discovered a truly marvelous proof of this theorem, but that the margin was too small to contain it. However, no proof of the theorem was found, and it became one of the most famous unsolved problems in mathematics for centuries. Fermat's last theorem is considered one of the earliest examples of a problem in number theory that was easy to state but extremely difficult to prove. The conjecture remained unproven for more than 3 centuries, despite efforts from many of the greatest mathematicians of the time, including Euler, Kummer, and Taniyama. Over the years, many partial results were established for specific values of n, and mathematicians showed that the theorem was true for several small values of n, but the general case for all values of n greater than 2 remained elusive. In 1993, the theorem was finally proven by the British mathematician Andrew Wiles. Wiles's proof was groundbreaking and utilized modern mathematical techniques that were not available to Fermat. His work involved a branch of mathematics called elliptic curves, which had been developed in the 20th century, and an important result known as the Taniyama-Shimura-Weyl conjecture. Wiles's proof of Fermat's last theorem was a major milestone in mathematics, not only because it solved the theorem, but also because it connected several previously unrelated areas of mathematics. His proof was incredibly complex and took many years to develop. It was initially announced in 1993 and was found to have a small gap in the argument. However, Wiles, with the help of his former student Richard Taylor, was able to fix the gap, and the final proof was published in 1994. The proof of Fermat's last theorem is extremely technical and spans several advanced areas of mathematics, including number theory, algebraic geometry, and modular forms. It represents a triumph of modern mathematics, and its resolution was celebrated worldwide. Despite the difficulty of the proof, Fermat's last theorem is important because it has deep implications for several areas of mathematics. It is linked to the study of Diophantine equations, which involve finding integer solutions to polynomial equations, and it has connections to the study of modular forms and elliptic curves, which are central topics in number theory. Fermat's last theorem is also a key result in the broader context of arithmetic geometry. a field of mathematics that studies solutions to polynomial equations with integer or rational coefficients. The theorem's proof also led to further developments in the theory of modular forms and elliptic curves, which have become central topics in modern mathematics. In fact, Wile's work on Fermat's last theorem was instrumental in proving the Taniyama-Shimura-Weil conjecture for a specific class of elliptic curves, which was a key part of the strategy used to prove the theorem. Fermat's last theorem has inspired many mathematicians and continues to be a source of fascination. The theorem's long history, the mystery surrounding Fermat's original claim of a proof, and the eventual resolution of the problem have made it a central story in the narrative of mathematics. It is a testament to the power of perseverance and the deep connections that exist between different areas of mathematics. In conclusion, Fermat's last theorem is a landmark result in mathematics that was first conjectured by Pierre de Fermat in the 17th century and remained unproven for over 300 years. It asserts that the equation x raised to the power of n plus y raised to the power of n equals z raised to the power of n has no solutions in positive integers for any n greater than 2. The theorem was finally proven by Andrew Wiles in 1994, using advanced techniques from modern mathematics. Wiles's proof of Fermat's last theorem is a major achievement in the history of mathematics and has had far-reaching implications for number theory, algebraic geometry, and related fields. The resolution of the theorem stands as a testament to the persistence of mathematical inquiry and the depth of connections within mathematics. Catalan's conjecture, also known as Mihailescu's theorem, is a famous result in number theory, proposed by the Belgian mathematician Eugène Charles Catalan in 1839. The conjecture is concerned with the powers of integers and their behavior in Diophantine equations. It states that the only solution to the equation, x raised to the power of a equals y raised to the power of b plus 1, where x, y, a, and b are positive integers, is the solution x equals 3, y equals 2, a equals 2, and b equals 3. In other words, the only solution to this equation, where both x and y are integer powers greater than 1, is the pair 3, 2, 2, 3. This conjecture was proposed by Catalan, and its proof remained one of the unsolved problems in mathematics for over a century. Catalan's conjecture is particularly interesting because it involves a simple equation involving powers, but the solution is quite unique. The equation essentially asks if there are any other pairs of integers that satisfy the equation, where both x and y are raised to a power greater than 1. Catalan's conjecture asserts that the pair 3, 2, 2, 3 is the only solution to this equation. The conjecture remained unproven for many years, despite efforts by many mathematicians. It was a difficult problem in number theory, and no one was able to find any other integer solutions to the equation. In fact, the conjecture had been a central question in the study of Diophantine equations for over 100 years. The breakthrough came in 2005, when the Hungarian mathematician László Mihailescu proved Catalan's conjecture. Mihailescu's proof was a major milestone in mathematics, and it finally resolved the conjecture. His proof demonstrated that the only solution to the equation is indeed the pair 3, 2, 2, 3, as Catalan had predicted. Mihailescu's proof was highly complex and used advanced techniques from algebraic number theory and Diophantine approximation. The proof was a culmination of efforts by many mathematicians over the years, and it relied on deep results in the theory of powers of integers, prime factorization, and the structure of Diophantine equations. Mihailescu's result showed that no other integer solutions existed for the equation, thereby confirming Catalan's original conjecture. Catalan's conjecture is closely related to other problems in number theory that involve powers of integers. It is particularly significant in the study of Mersenne numbers and Fermat numbers, both of which are related to powers of integers. The conjecture also ties into the study of exponential Diophantine equations, which are equations involving powers and products of integers. Catalan's conjecture is a specific case of these broader types of Diophantine problems, and was one of the earliest conjectures in the field to be definitively resolved. The proof of Catalan's conjecture has had implications for the broader study of Diophantine equations and number theory. It demonstrated that very specific properties of integers and powers constrain the solutions to certain types of Diophantine equations. Mihailescu's proof provided new insights into the behavior of powers of integers and the relationships between different types of Diophantine equations, which continue to be an active area of research in mathematics. Catalan's conjecture is sometimes referred to as a special case of Fermat's last theorem, because it deals with powers of integers and involves a specific equation similar to those studied in Fermat's last theorem. However, while Fermat's last theorem concerns solutions to the equation x raised to the power of n plus y raised to the power of n equals z raised to the power of n for n greater than 2, Catalan's conjecture is much more specific, dealing with a very particular case of powers and additions. In conclusion, Catalan's conjecture was an important and long-standing problem in number theory, proposed by Eugène-Charles Catalan in the 19th century. It asserts that the only solution to the equation x raised to the power of a equals y raised to the power of b plus 1, with both x and y raised to powers greater than 1, is the pair 3, 2, 2, 3. The conjecture remained unsolved for over a century, until it was finally proven by Laszlo Mihailescu in 2005. Mihailescu's proof relied on deep results in algebraic number theory and Diophantine equations, and it resolved the conjecture, confirming that the pair 3, 2, 2, 3 is indeed the only solution. Catalan's conjecture is a significant result in the study of Diophantine equations and powers of integers, and has contributed to the development of modern number theory. Hilbert's 10th problem is one of the most famous unsolved problems in the field of mathematical logic and number theory. It was posed by the German mathematician David Hilbert in 1900 and was part of his famous list of 23 unsolved problems. The problem asks for a general algorithm to determine whether a Diophantine equation has an integer solution. A Diophantine equation is an equation where the variables are required to take integer values, and the problem is to determine whether there exist integer solutions to such equations. In other words, Hilbert's 10th problem asks whether there is an algorithm that can take any Diophantine equation as input, and, after a finite number of steps, determine whether the equation has a solution in integers. While this problem appeared to be simple and straightforward, it turned out to be much more complex than anyone initially imagined, and its resolution had profound implications for the foundations of mathematics. At the time Hilbert posed his problem, mathematicians believed that it might be possible to find such an algorithm. This belief was based on the hope that all problems about the solvability of Diophantine equations could be reduced to systematic procedures or algorithms. The goal was to show that there exists a method, or algorithm, that would, for any given Diophantine equation, decide whether there is a solution. However, in the 1970s it was shown that Hilbert's 10th problem has a negative answer. In particular, the problem was proven to be undecidable, meaning that there is no general algorithm that can solve all Diophantine equations. This was established by the Soviet mathematician Julia Robinson, and later by Martin Davis, Hilary Putnam, and John Presburger. They proved that the problem is equivalent to a more general class of problems in logic, known as undecidable problems. Their work showed that it is impossible to create a procedure that would solve all Diophantine equations, no matter how complex the equation may be. The proof that Hilbert's 10th problem is undecidable came as a result of several groundbreaking developments in mathematical logic and computability theory. Specifically, the work of Davis, Putnam, and Robinson demonstrated that solving the general case of Diophantine equations would require solving the halting problem, which is a well-known undecidable problem in the theory of computation. The halting problem asks whether a given computer program will eventually halt, finish execution, or continue running indefinitely. This problem was proven to be undecidable by Alan Turing in the 1930s. The connection between Diophantine equations and the halting problem was established by demonstrating that a solution to Hilbert's 10th problem could be used to solve the halting problem. Because the halting problem is undecidable, it follows that Hilbert's 10th problem is also undecidable. The proof of undecidability was a significant result in the history of mathematics, as it showed the inherent limitations of algorithmic methods in solving mathematical problems. This result was part of the broader development of computability theory and recursive function theory, which sought to understand the limits of computation and the scope of mathematical problems that can be solved by algorithms. Despite the negative resolution of Hilbert's 10th problem, the study of Diophantine equations continues to be an active area of research. While there is no general algorithm to solve all Diophantine equations, mathematicians have developed methods and techniques to find solutions to many specific types of Diophantine equations. For example, elliptic curve theory and modular forms have provided powerful tools for solving certain classes of Diophantine equations, especially in the context of Fermat's last theorem and other important results in number theory. The undecidability of Hilbert's 10th problem also led to further research into the structure of undecidable problems in mathematics and logic. The field of mathematical logic and computability theory has expanded significantly since the problem was posed, and the study of which problems are decidable and which are undecidable remains a central concern in the foundations of mathematics. The Gaussian Moat problem is a geometric problem in the field of mathematics that is related to the distribution of points on the Gaussian plane, which is a two-dimensional plane consisting of complex numbers. The problem involves determining the distribution of points on this plane that are located at integer coordinates, also known as lattice points, and investigating how they are arranged relative to a circle centered at the origin. The problem can be stated as follows. Consider the Gaussian integers, which are complex numbers of the form a plus bi, where a and b are integers, and I is the imaginary unit, satisfying I squared equals -1. The problem asks about the number of Gaussian integers that lie within a certain distance from the origin, as well as the geometry of the lattice formed by these points. The central question of the problem is to determine how many lattice points lie within a given circle in the Gaussian plane, and how these points are distributed relative to the circle's boundary. The problem is particularly interesting because it combines elements of number theory and geometry. The lattice points in the Gaussian plane form a regular grid with points spaced 1 unit apart. The circle, however, is not constrained to lie on this regular grid, and this creates a rich structure of points inside and on the boundary of the circle. The question is essentially about counting the number of lattice points that fall within or on the boundary of a given circle, and whether there are any interesting patterns or properties of these points. One of the key ideas in the Gaussian moat problem is the concept of the Gaussian moat, which refers to the region between the boundary of the circle and the lattice points that are closest to it. The moat is the region where there are no lattice points, and its width is a measure of how densely the lattice points are packed near the boundary of the circle. The Gaussian moat is important because it helps describe how the lattice points are distributed in the Gaussian plane, and whether there is any significant empty space around the circle before reaching the nearest lattice point. The problem has connections to other areas of mathematics, including analytic number theory, geometry, and lattice theory. It also relates to the study of circle packing and Diophantine approximation, where mathematicians study the distribution of points in various geometric settings. In particular, the Gaussian Moat problem is related to the study of approximating real numbers by rational numbers and the geometry of lattice point distributions in higher dimensional spaces. While the problem has not been completely solved in a general form, it has led to a number of important discoveries and partial results. One of the key results is that as the radius of the circle increases, the number of lattice points inside the circle grows roughly in proportion to the area of the circle, which is proportional to the square of the radius. This result is consistent with the density of lattice points in the Gaussian plane, which is evenly distributed over the plane as a whole. However, there are still open questions about the precise behavior of the Gaussian moat and how the lattice points are distributed near the boundary of the circle. In conclusion, the Gaussian moat problem is a geometric and number-theoretic problem that involves counting the number of Gaussian integers, lattice points within a circle in the complex plane. The problem also explores the region around the circle, called the Gaussian moat, where no lattice points are present. The problem connects several areas of mathematics, including geometry, number theory, and lattice theory, and it has led to important insights about the distribution of lattice points in the Gaussian plane. Although the problem remains unsolved in general, it continues to be an area of active research in mathematics. Legendre's conjecture is a famous unsolved problem in number theory, proposed by the French mathematician Adrien-Marie Legendre in the late 18th century. The conjecture is related to the distribution of prime numbers, which are numbers greater than 1 that are only divisible by 1 in themselves. Prime numbers play a crucial role in many areas of mathematics, and understanding their distribution has been a central topic of study in number theory for centuries. The conjecture itself is a statement about the gaps between consecutive prime numbers. Specifically, Legendre's conjecture asserts that there is always at least one prime number between every consecutive pair of perfect squares. In other words, for any integer n, there exists at least one prime number p such that n squared p n plus 1 squared. This statement implies that the primes are not too far apart from one another, as there is always a prime number in every gap between consecutive perfect squares. The conjecture was proposed as a way to explore the distribution of primes and their spacing as numbers grow larger. Legendre's conjecture is significant because it is related to the prime number theorem, which describes the asymptotic distribution of prime numbers. The prime number theorem, proven by Hadamard and de la Vallée-Poussin in the late 19th century, states that the number of primes less than or equal to a given number x is approximately equal to x divided by the natural logarithm of x. This result provides a rough estimate of how primes are distributed across the number line. However, Legendre's conjecture is more specific and provides a stronger statement about the distribution of primes. It focuses on the spacing between consecutive primes, asserting that the primes cannot be too distant from each other within the intervals defined by consecutive perfect squares. Despite the conjecture being simple to state, proving it has proven to be a difficult task for mathematicians. As of now, Legendre's conjecture remains unproven, but there has been significant progress in related areas. One of the key results that provide evidence for the conjecture is the prime gap theorem, which states that the gaps between consecutive primes can be arbitrarily large, but this does not directly contradict Legendre's conjecture. The prime gap theorem shows that, although the gaps between primes can grow larger as the numbers increase, they are not so large as to prevent a prime from existing between two consecutive perfect squares. In fact, the conjecture is related to another important unsolved problem in number theory called the Riemann conjecture, which gives a conjectural upper bound on the size of prime gaps. Kramer's conjecture suggests that the gap between consecutive primes p and q satisfies the inequality E log p more 2, which would imply that prime gaps grow relatively slowly compared to the size of the primes themselves. This result would support Legendre's conjecture by implying that the gaps between primes are not large enough to skip over the interval between consecutive perfect squares. Another related result is Bertrand's postulate, proven by Pafnuty-Chebyshev in 1852, which states that for any integer n greater than 1, there is always at least one prime number p, such that n less than p less than 2n. Although Bertrand's postulate does not directly imply Legendre's conjecture, it does demonstrate the tendency of prime numbers to appear in close proximity to one another. Despite these partial results and related conjectures, Legendre's conjecture itself has not been proven or disproven, and it remains an open question in number theory. The problem has captured the interest of mathematicians for more than 200 years, and its resolution would provide important insights into the distribution of primes and the structure of the integers. In conclusion, Legendre's conjecture is a significant and long-standing problem in number theory that posits there is always at least one prime number between every pair of consecutive perfect squares. While the conjecture has not been proven, it has been the subject of much research, and is closely related to other important results and conjectures about prime numbers, including the prime number theorem and Kramer's conjecture. The conjecture reflects the deep and mysterious properties of prime numbers and their distribution, and its resolution would represent an important advancement in understanding the behavior of primes. Mertens conjecture is a conjecture in number theory, proposed by the German mathematician Franz Mertens in 1874. The conjecture is concerned with the behavior of the Mertens function, which is defined in relation to the prime numbers and plays an important role in analytic number theory. The Mertens function is the cumulative sum of the Liouville function, which is a multiplicative function associated with the prime factorization of integers. The Liouville function is defined as Liouville function of n equals -1 raised to the power of the number of distinct prime factors of n. The Mertens function is then given by the sum of the Liouville function for all integers up to n. Mertens function of n equals the sum of the Liouville function of k for all k from 1 to n. The Mertens conjecture itself makes a statement about the growth of the Mertens function as n increases. Specifically, it conjectures that the absolute value of the Mertens function grows no faster than the square root of n. That is, it posits that the absolute value of Mertens function of n is less than the square root of n for all n greater than or equal to 1. This conjecture suggests that the Mertens function is bounded in a certain sense, and it implies that the Mertens function does not grow too quickly as n increases. In other words, the conjecture predicts that the cumulative sum of the Liouville function, when taken up to any given integer, will not exceed the square root of that integer. The Mertens conjecture was proposed in the context of studying the distribution of prime numbers and their effects on number-theoretic functions. The conjecture was attractive to mathematicians because it was related to deep questions about the behavior of primes and their distribution, and it made a precise statement about the growth of a function that depended on the prime factorization of integers. For many years, the Mertens conjecture was widely believed to be true, and it was supported by numerical evidence for large values of n. However, despite extensive computations and research, the conjecture was proven false in 1999 by the mathematician Harold Helfgott. Helfgott showed that the Mertens conjecture does not hold, providing a counterexample that demonstrated that the Mertens function can grow faster than the square root of n. The result by Helfgott showed that the Mertens function does not satisfy the inequality. The absolute value of Mertens function of n is less than the square root of n for all n, as the conjecture had proposed. Instead, it was shown that the Mertens function can grow asymptotically faster than the square root of n, which means that the growth of the function is more erratic and not as tightly bounded as the conjecture had suggested. Despite the fact that the Mertens conjecture was proven false, the study of the Mertens function and related questions about the distribution of prime numbers remains an important area of research in number theory. The behavior of the Mertens function has deep connections to other important results in analytic number theory, such as the Riemann hypothesis, which is one of the most famous and long-standing open problems in mathematics. In particular, the Mertens function is closely related to the Riemann zeta function, which encodes information about the distribution of primes. Although the Mertens conjecture was disproven, the exploration of prime number distribution continues to be a crucial and active area of research in mathematics. Brouwer fixed-point theorem is a fundamental result in topology, a branch of mathematics that deals with the properties of space that are preserved under continuous deformations. The theorem is named after the Dutch mathematician Luitzen Egbertus Jan Brouwer, who proved it in the early 20th century. It is one of the most important results in the field of topological fixed-point theory, which is concerned with understanding the conditions under which a function has a fixed point. The Brouwer fixed-point theorem states that for any continuous function that maps a compact convex set to itself, there must be at least one point in the set that is mapped to itself. In simpler terms, the theorem asserts that if you take any closed, bounded region in space, called a compact convex set, and apply a continuous function to that region, there will always be a point in that region which remains unchanged after the function is applied. The most common example used to illustrate the theorem is the case of a disk in the two-dimensional plane. If you take a disk and apply any continuous transformation to it, the theorem guarantees that there will be at least one point in the disk that does not move. This result has important implications in many areas of mathematics, economics, and various fields of science, particularly in problems involving equilibrium and stability. In more formal terms, the theorem applies to Euclidean spaces, meaning that the set in question is a subset of some Euclidean space, such as the plane or three-dimensional space. The set must be compact, closed and bounded, and convex, meaning that any 2 points within the set can be connected by a straight line that lies entirely within the set. The function in question must also be continuous, meaning that small changes in the input will result in small changes in the output. The fixed point refers to a point in the set where the function maps it to itself. If such a point exists, the function is said to have a fixed point. The Brouwer fixed-point theorem asserts that for a wide class of functions, there is always at least one fixed point, regardless of the specifics of the function or the set, as long as the function is continuous and the set is compact and convex. A special case of the theorem is the special case of the unit disk in the plane, where the theorem states that any continuous function from the unit disk to itself must have at least one fixed point. This result has applications in fields like economics, game theory, and optimization, where fixed-point theorems are used to prove the existence of equilibria and solutions to optimization problems. The Brouwer fixed-point theorem is a key result in the study of topological dynamics, which studies the behavior of systems over time under continuous transformations. The theorem is also important in the study of nonlinear analysis, as many problems in this area involve finding fixed points of functions, which can be interpreted as solutions to equations or equilibrium states of a system. In addition to its existence result, the Brouwer fixed-point theorem also leads to important results in the theory of dynamical systems and game theory, where it is used to prove the existence of Nash equilibria. A Nash equilibrium is a state in a game where no player can improve their situation by changing their strategy, and the existence of such an equilibrium is guaranteed by the Brouwer fixed-point theorem. While the Brouwer fixed-point theorem is mainly concerned with the existence of fixed points, it does not necessarily provide information about the uniqueness of the fixed point. The theorem guarantees that there is at least one fixed point, but it does not guarantee that there is only one. In fact, many functions that satisfy the conditions of the theorem can have multiple fixed points. The uniqueness of the fixed point is a more complex issue and depends on additional conditions. For example, if the function is contractive, i.e., it brings points closer together, then the Banach fixed-point theorem guarantees the existence of a unique fixed point. In contrast, the Brouwer fixed-point theorem only assures the existence of a fixed point, not its uniqueness. In conclusion, the Brouwer fixed-point theorem is a significant result in topology that states that any continuous function mapping a compact convex set to itself has at least one fixed point. This theorem has wide applications in mathematics, economics, game theory, and many other fields, as it guarantees the existence of equilibrium solutions in various situations. While it does not address the uniqueness of the fixed point, the theorem plays a crucial role in understanding the behavior of continuous functions and the dynamics of systems. The Continuum Hypothesis is one of the most famous and long-standing problems in set theory, a branch of mathematical logic that deals with the study of sets or collections of objects. The hypothesis concerns the size of infinity and attempts to understand the relationship between different sizes of infinite sets. It was proposed by the German mathematician Georg Cantor in the late 19th century, who is known for his groundbreaking work in the theory of infinite sets. The Continuum Hypothesis, often abbreviated as CH, deals with the cardinality or size of sets, specifically the set of real numbers. In Cantor's framework, the set of natural numbers, 1, 2, 3, etc., is considered the smallest infinite set, and its cardinality is referred to as aleph null. The real numbers, which include all rational and irrational numbers, are a larger set, and their cardinality is represented by C, known as the cardinality of the continuum. The Continuum Hypothesis asserts that there is no set whose cardinality is strictly between the cardinality of the natural numbers and the cardinality of the real numbers. In other words, the hypothesis proposes that there are no sizes of infinity between aleph null and C. This can be expressed as: there is no set A such that aleph null is less than the cardinality of A, and the cardinality of A is less than the cardinality of the continuum. This means that the cardinality of the continuum is the next larger size of infinity, after that of the natural numbers, and there are no infinite sets whose size lies between these two cardinalities. The Continuum Hypothesis is concerned with the question of whether such a set can exist or not. Cantor's work on the Continuum Hypothesis was part of his broader investigation into the structure of infinite sets and the development of transfinite numbers, which extend the concept of counting beyond finite and infinite sets. He proved that there are many different sizes of infinity, and he introduced the idea of comparing the sizes of different infinite sets. However, he was unable to resolve the specific question of whether there is a set of size strictly between the natural numbers and the real numbers. For many years, the Continuum Hypothesis remained an open question in mathematics. It became a central topic of research in set theory, and mathematicians sought to prove or disprove it. However, in the mid-20th century, two significant developments occurred that changed the way the Continuum Hypothesis was viewed. First, Kurt Gödel, in the 1940s, showed that the Continuum Hypothesis cannot be disproven using the standard axioms of set theory, known as Zermelo-Fraenkel set theory with the axiom of choice, or ZFC. He demonstrated that if the Zermelo-Fraenkel set theory is consistent, then the continuum hypothesis cannot be contradicted within this framework. In other words, Gödel showed that it is consistent with the axioms of set theory that there is no set with a cardinality between Aleph null and the cardinality of the continuum. Then, in the 1960s, the mathematician Paul Cohen proved the reverse. He showed that it is also consistent with the axioms of set theory to assume that the continuum hypothesis is false. Cohen used a technique known as forcing, which allows mathematicians to construct new models of set theory in which certain statements can be true or false. Using forcing, Cohen demonstrated that there are models of set theory in which the continuum hypothesis does not hold, meaning that there can be a set with a cardinality between Aleph null and the cardinality of the continuum. Together, these results, Gödel's proof of consistency and Cohen's proof of independence, showed that the continuum hypothesis cannot be proven or disproven using the standard axioms of set theory. This means that the continuum hypothesis is independent of the Zermelo-Fraenkel axioms with the axiom of choice, meaning that both the statement and its negation are consistent with these axioms. The fact that the continuum hypothesis is independent of the standard axioms of set theory implies that mathematicians are free to adopt either version of the hypothesis, whether it is true or false, depending on the framework they are working in. This has led to the idea that the continuum hypothesis may not have a definitive truth value in the context of conventional set theory. Waring's problem is a famous problem in the field of number theory, proposed by the English mathematician David Waring in the 18th century. It concerns the representation of natural numbers as sums of powers of natural numbers. Specifically, the problem asks whether every natural number can be expressed as the sum of a fixed number of powers of natural numbers. The problem was first formulated by Waring in his work Méditation algébrique in 1770. Waring's problem can be described as follows. For each natural number k, there exists a minimum number g e she k, such that every natural number is the sum of at most ek kth powers of natural numbers. The goal is to find this number g of k for various values of k. In simpler terms, the problem asks if it is possible to express every natural number as the sum of a fixed number of powers of integers. The exponent of the powers can vary, and the question is whether such representations exist for all natural numbers, and if so, how many powers are needed. Waring's conjecture, which is the statement made by Waring in his work, claims that for each integer k, there exists a natural number g of k such that every natural number is the sum of at most gkth powers. The conjecture suggested that for each k, it is possible to find a fixed upper bound for the number of terms in the sum. For example, for k equals 2, the problem becomes expressing natural numbers as sums of squares, and Waring's conjecture suggested there is a fixed upper bound for the number of squares needed to express any natural number. In the case of k equals 2, the problem reduces to the question of representing natural numbers as sums of squares. It was shown by Lagrange in 1770 that every natural number can be expressed as the sum of at most 4 squares. This result is known as Lagrange's 4-square theorem. The result provides an answer for the case when k equals 2, confirming that every natural number can indeed be expressed as the sum of at most 4 squares, and therefore the number g of 2 equals 4. For higher values of k, the problem is more complicated. In general, the exact values of g of k are not known for all values of k, and finding these values remains an active area of research in number theory. It was shown by Hilbert and others that g of k exists for all values of k, but the exact values of g of k are difficult to determine. For example, for k equals 3, it was shown that every natural number can be written as the sum of at most 9 cubes, and this result was established by Hardy and Wright in their work on number theory. As k increases, the values of g of k tend to grow larger, and it becomes increasingly difficult to determine exact values. In some cases, only upper bounds for gk are known, and these upper bounds can be quite large. Despite these challenges, Waring's problem has been a central topic in number theory and has led to many significant results and further research in the field. The inverse Galois problem is a fundamental question in the field of algebraic number theory and field theory. The problem is named after the French mathematician Évariste Galois, who developed the theory of Galois groups in the 19th century. The problem essentially asks whether every finite group can be realized as the Galois group of a Galois extension of the field of rational numbers, or more generally, over any given base field. To understand the inverse Galois problem, it is necessary to first grasp some basic concepts from Galois theory. A Galois group is a group associated with a field extension. Specifically, if you have a field extension, the Galois group describes the symmetries of the extension. It represents the set of automorphisms, or isomorphisms, of the field extension that leave the base field unchanged. These automorphisms can be thought of as the ways in which the elements of the extension field can be mapped to one another, while still respecting the structure of the field. For example, the Galois group of a polynomial is the group of permutations of its roots that preserve the structure of the field. A classical result in Galois theory is that the Galois group of a splitting field of a polynomial is a group that describes how the roots of the polynomial can be transformed into one another. The inverse Galois problem asks whether, for any given finite group, there exists a Galois extension of the rational numbers, or any base field, whose Galois group is isomorphic to that group. In simpler terms, the problem asks whether any finite group can appear as the symmetry group of some field extension of rational numbers. To make this more concrete, consider a finite group such as the symmetric group or the alternating group, and ask whether it is possible to find a polynomial with rational coefficients whose Galois group is exactly that group. The inverse Galois problem seeks to determine whether such polynomials can always be found for any finite group. While Galois groups have been extensively studied, and many specific instances of the inverse Galois problem have been solved, a complete solution to the problem remains elusive. The problem is considered one of the central questions in the field of Galois theory and field theory, and it has deep connections to various areas of mathematics, including algebraic geometry, algebraic topology, and arithmetic geometry. In the 20th century, the study of the inverse Galois problem has made substantial progress, particularly in the case of solvable groups, abelian groups, and groups of small order. In fact, it has been shown that every solvable finite group can be realized as the Galois group of some Galois extension of the rational numbers. However, for general finite groups, much less is known. One of the key challenges in solving the inverse Galois problem is the difficulty in constructing explicit Galois extensions with a prescribed Galois group. The problem requires finding field extensions whose Galois groups have very specific properties, and this is often a very difficult task. Moreover, there are additional complications when dealing with non-abelian groups or groups of large order, where the methods used to construct Galois extensions are more complex. The inverse Galois problem is closely related to the study of explicit constructions of field extensions. These constructions often involve sophisticated tools from algebraic geometry, number theory, and arithmetic. The search for solutions to the inverse Galois problem has led to the development of new techniques in these areas, as mathematicians have attempted to find ways to construct field extensions with given Galois groups. In summary, the inverse Galois problem asks whether every finite group can be realized as the Galois group of a Galois extension of a base field, typically the field of rational numbers. While significant progress has been made for certain types of groups, a complete solution to the problem remains an open question in mathematics. The problem is a central topic in the study of Galois theory and has connections to many areas of mathematics, making it one of the most intriguing and challenging problems in modern algebra. The Jacobian conjecture is a famous open problem in the field of algebraic geometry, proposed by the mathematician Oskar Zariski in the 1940s. It is concerned with the structure of polynomial maps in several variables, specifically focusing on the invertibility of these maps. The conjecture has significant implications for algebraic geometry, the theory of singularities, and the study of polynomial functions. In simple terms, the Jacobian conjecture is a statement about polynomial maps from n-dimensional space to n-dimensional space, where both the domain and the codomain are over the field of complex numbers or other algebraically closed fields. The conjecture asserts that a certain type of polynomial map, called a local invertible map, is actually globally invertible. The problem can be stated more precisely as follows. Consider a polynomial map from n-dimensional space, denoted as c to the power of n, to n-dimensional space. The map is defined by a collection of polynomial functions in n variables. Let the map be given by n polynomials in n variables, and suppose that the Jacobian determinant of this map is a non-zero constant. The Jacobian matrix is a matrix of partial derivatives of the polynomial functions that define the map. The determinant of this matrix, known as the Jacobian determinant, plays a crucial role in determining whether the map is invertible. The Jacobian conjecture states that if the Jacobian determinant of the map is a non-zero constant, then the map itself is invertible, and the inverse map is also a polynomial map. In other words, if the map has a constant non-zero Jacobian determinant, it should be an isomorphism, meaning there exists a polynomial map that can reverse the original map. This conjecture is particularly interesting because, in general, even if a map is locally invertible, which means it has an inverse in small neighborhoods of points, it does not guarantee that the map is globally invertible. The Jacobian conjecture suggests that for polynomial maps with a constant non-zero Jacobian determinant, the map is not only locally invertible, but it is globally invertible as well, with the inverse also being a polynomial map. One of the main challenges of the Jacobian conjecture lies in the fact that it is a very general statement about polynomial maps. While specific cases have been solved, the general case remains open. The conjecture has been the subject of much research over the years, and numerous partial results have been obtained, but a complete proof of the conjecture is still elusive. In the decades following Zariski's proposal of the conjecture, several mathematicians have made important contributions to the study of the Jacobian conjecture. For example, it has been proven for dimension 2, meaning that if a polynomial map in two variables has a constant non-zero Jacobian determinant, then the map is invertible, and its inverse is also a polynomial. However, for dimensions greater than 2, the conjecture remains open and has resisted proof. The conjecture has also inspired the study of related problems in algebraic geometry, such as the invertibility of polynomial maps and the classification of certain types of algebraic varieties. It has connections to the theory of algebraic groups, singularity theory, and differential geometry, as well as the study of affine varieties, which are solutions to systems of polynomial equations. Over the years, mathematicians have developed many techniques in their attempts to solve the Jacobian conjecture. These include methods from algebraic topology, commutative algebra, and singularity theory. Despite the many efforts, a general proof or disproof of the conjecture is still an open problem in mathematics. In summary, the Jacobian conjecture posits that a polynomial map in n variables with a non-zero constant Jacobian determinant is invertible and has a polynomial inverse. While the conjecture has been proven in special cases, it remains an unsolved problem in algebraic geometry. The conjecture continues to be a topic of intense study, and is one of the most important open problems in the field. Hilbert's first problem, one of the famous 23 problems proposed by David Hilbert in 1900, concerns the continuum hypothesis and the nature of infinite sets. Hilbert's first problem can be stated as follows. It asks whether there is a set whose cardinality is strictly between that of the natural numbers and the real numbers. In other words, the problem is concerned with understanding the sizes of infinite sets, and whether there is a set that is larger than the set of natural numbers, but smaller than the set of real numbers in terms of cardinality. To understand the problem, we need to delve into set theory and the concept of cardinality, which refers to the size of a set. The cardinality of a set is a measure of how many elements it contains. For finite sets, this is just the number of elements in the set. For infinite sets, however, things are more complicated. The two most famous infinite sets are the set of natural numbers, which has cardinality aleph null, also called countable infinity. The set of real numbers, which has a larger cardinality known as the cardinality of the continuum. Hilbert's first problem asks whether there is an infinite set whose cardinality is strictly between these two, i.e., whether there exists an infinite set that is larger than natural numbers but smaller than real numbers. In modern terminology, this question is closely related to the continuum hypothesis. The continuum hypothesis, proposed by Georg Cantor in the late 19th century, asserts that no such set exists. That is, it states that there is no set whose cardinality lies strictly between that of the natural numbers and the real numbers. In other words, the cardinality of the continuum is the next cardinality after aleph null, and there is no set whose cardinality is between aleph null and the cardinality of the continuum. In the early 20th century, Hilbert's first problem became a major topic of research in set theory. However, Kurt Gödel and Paul Cohen independently showed that the continuum hypothesis cannot be proven or disproven using the standard axioms of set theory, known as Zermelo-Fraenkel set theory with the axiom of choice, or ZFC. This means that the continuum hypothesis is independent of the standard axioms of set theory. It is neither provable nor disprovable within the standard framework of mathematics. Gödel showed in 1938 that the continuum hypothesis is consistent with ZFC, meaning that it can be assumed true without leading to a contradiction. And Cohen showed in 1963 that it is consistent with its negation, meaning that it can also be assumed false without leading to a contradiction. Thus, the answer to Hilbert's first problem is that it depends on the specific set-theoretic model we adopt. The continuum hypothesis may either be true or false, but it cannot be settled using the standard axioms of set theory alone. The impact of Hilbert's first problem is profound, as it highlighted the limitations of set theory and the need to examine the foundations of mathematics more deeply. The work of Gödel and Cohen on the continuum hypothesis has led to the development of new areas of study in mathematical logic, model theory, and mathematical foundations. In summary, Hilbert's first problem asks whether there exists an infinite set with cardinality between that of the natural numbers and the real numbers. This question is intimately tied to the continuum hypothesis, which has been shown to be independent of the standard axioms of set theory, meaning it can neither be proven nor disproven within the standard framework of mathematics. The problem remains an important part of the study of set theory and the foundations of mathematics. Szemerédi's theorem is a profound result in the field of additive number theory, proposed by the Hungarian mathematician Endre Szemerédi in 1975. The theorem addresses the question of how often arithmetic progressions appear within sets of integers, and gives a precise answer for sufficiently large sets. The theorem has deep connections to other areas of mathematics, such as combinatorics, ergodic theory, and Ramsey theory, and is a cornerstone result in the study of structured subsets of integers. In its simplest form, Szemerédi's theorem states that for any positive integer k, any subset of the natural numbers with positive density contains an arithmetic progression of length k. An arithmetic progression is a sequence of numbers where the difference between consecutive terms is constant. For example, the sequence 3, 6, 9, 12 is an arithmetic progression with common difference 3. To understand the theorem, let's break down its components. Density of a set. The density of a set A of natural numbers is defined as the limit of the proportion of elements of A among the first n natural numbers, as n goes to infinity. More formally, the density is the limit of the ratio of the number of elements of A in the set, 1, 2, n to n, as n tends to infinity. If this ratio is positive, the set is said to have positive density. Arithmetic progression of length, e-k. An arithmetic progression of length k is a sequence of k numbers of the form a, apseed, apuded, k1d, where a is the first term, and d is the common difference. Szemerédi's theorem asserts that if you have a subset of the natural numbers that has positive density, you can always find an arithmetic progression of length k within that set. This means that no matter how the set is structured, as long as it contains a large enough proportion of integers, there will always be an arithmetic progression of any given length. For example, if you take any sufficiently large subset of the natural numbers, say the set of all even numbers, it will always contain an arithmetic progression of any length, such as 2, 4, 6, 8. The significance of Szemerédi's theorem lies in its generality and its application to various branches of mathematics. It generalizes a number of earlier results in additive number theory, including the famous van der Waerden's theorem, which concerns the existence of monochromatic arithmetic progressions in any coloring of the natural numbers. Szemerédi's theorem extends this idea to arbitrary sets with positive density and any length of arithmetic progression. Szemerédi's theorem was a groundbreaking result because it answered a long-standing question in number theory. For many years, mathematicians had been trying to understand how often arithmetic progressions appear in subsets of integers. Szemerédi's theorem showed that such progressions are inevitable when the set has positive density, and this was a major breakthrough in the field of additive combinatorics. The proof of Szemerédi's theorem is highly non-trivial and relies on a combination of advanced techniques from several areas of mathematics. The original proof was completed by Szemerédi in 1975, and it used ergodic theory and graph theory to establish the result. In the years following, several other proofs of the theorem were discovered, some of which involved even more advanced methods, such as Fourier analysis and hypergraph theory. One of the key ideas in the proof is the use of regularity lemma, a combinatorial tool that helps to analyze the structure of large graphs and sets. This tool allows mathematicians to break down the set into smaller, more manageable pieces, making it easier to identify arithmetic progressions. Szemerédi's theorem has many important consequences and applications in both pure and applied mathematics. It has led to further developments in additive combinatorics, the study of uniformity in random structures, and the investigation of the structure of integers. Additionally, it has influenced other areas of mathematics, such as ergodic theory, graph theory, and probability theory. In summary, Szemerédi's theorem is a central result in additive number theory that states that any subset of the natural numbers with positive density contains an arithmetic progression of any desired length. The theorem has wide-ranging implications in mathematics and has influenced many areas, including combinatorics, ergodic theory, and Ramsey theory. the proof of the theorem was a landmark achievement and has led to the development of powerful mathematical techniques used to study structured sets and arithmetic progressions. Ulam's conjecture, proposed by the Polish-American mathematician Stanisław Ulam in the 1950s, is a problem in the field of number theory that deals with the distribution of integers in certain mathematical sets. It is concerned with the representation of even numbers as the sum of two primes, and while it may sound similar to the Goldbach conjecture, it has a distinct focus and context. The conjecture can be stated as follows. Ulam's conjecture asserts that every even number greater than 2 can be expressed as the sum of two primes, p and q, in exactly one way, meaning that there are no other distinct pairs of primes that add up to the same even number. To clarify, for any even integer n, there exists a pair of prime numbers p and q such that n equals p plus q. However, Ulam's conjecture takes this further by stating that each even number can be expressed in this way in exactly one unique way. In other words, no two different pairs of prime numbers should sum up to the same even number. If two distinct pairs of primes existed that could sum up to the same even number, Ulam's conjecture would be disproven. For example, for the number 4, the only representation as the sum of two primes is 2 plus 2, which is valid and unique. Similarly, 6 can only be expressed as 3 plus 3, and 8 can only be expressed as 3 plus 5. While Ulam's conjecture is similar in spirit to the Goldbach conjecture, which states that every even number greater than 2 can be expressed as the sum of two primes, but does not require uniqueness. Ulam's conjecture adds an extra constraint by requiring that the decomposition be unique for each even number. Despite its simplicity, the conjecture remains unresolved. There has been no counterexample found to disprove it, but neither has a general proof been established. This problem is part of the ongoing study of prime numbers and the ways in which they combine to form other integers. Ulam's conjecture has connections to the Goldbach conjecture, but it also has implications in other areas of mathematics, especially in the study of combinatorics and the behavior of prime numbers within mathematical structures. Though Ulam's conjecture remains unproven, it remains an interesting and thought-provoking problem in number theory, illustrating the deep and intricate relationships between prime numbers and the integers they sum to. In summary, Ulam's conjecture is a mathematical hypothesis that every even number greater than 2 can be expressed as the sum of two primes in exactly one way. Although it shares similarities with the Goldbach conjecture, it places the additional constraint of uniqueness on the prime pairs. The conjecture remains unproven to this day, and its resolution would represent a significant breakthrough in the understanding of prime number sums. Goormaghigh's conjecture is a problem in the field of number theory, named after the Belgian mathematician Jean Goormaghtigh, who proposed it in 1953. The conjecture is related to the distribution of prime numbers and their powers. Specifically, it concerns the sum of powers of prime numbers and poses a question about their behavior in relation to integers. The conjecture states the following. If a number can be written as the sum of two powers of prime numbers, it can only be written in one way. In more formal terms, Goormaghigh's conjecture suggests that if an integer n can be expressed as the sum of two distinct powers of prime numbers, i.e., n equals p to the power of a plus, qb, where p and q are primes and a and b are positive integers, there will be no other combination of primes p and q such that the equation in Hypothesis by 8qb holds. This means that the decomposition of n into the sum of two prime powers is unique. For example, if n equals 10, it can be written as 2 to the power of 1 plus 3 squared, which gives 10 equals 2 plus 3, 9. According to Goormaghigh's conjecture, there would be no other combination of primes and powers that sums to 10. The conjecture remains an open problem in mathematics. While it has been checked for many integers and found to hold, a general proof for all integers or a counterexample remains elusive. The conjecture is of interest because it involves the sum of prime powers, which is a relatively simple operation but leads to complex and often unpredictable behavior when applied to large numbers. One of the key challenges in proving or disproving Goormaghigh's conjecture lies in the difficulty of understanding the distribution of prime numbers, especially their higher powers, and how these powers combine to form other integers. Prime numbers exhibit highly irregular patterns, and understanding their behavior when raised to different powers or combined in sums is a challenging task in modern number theory. Goormaghigh's conjecture has connections to other problems in additive number theory, where mathematicians study the ways in which integers can be written as sums of different mathematical objects, such as squares, cubes, and prime powers. This area of research is deeply connected to the study of prime number theory, Diophantine equations, and additive combinatorics. In summary, Goormaghigh's conjecture is a number-theoretic hypothesis that suggests that any integer that can be written as the sum of two prime powers has a unique representation. The conjecture is still unproven, and its resolution would deepen our understanding of the distribution of prime numbers and their powers in relation to integers. The Erdős-Strauss conjecture is a famous open problem in number theory, proposed by the Hungarian mathematicians Paul Erdős and Ernst Strauss in 1948. The conjecture concerns the representation of the fraction 4 over n as a sum of three positive fractions, each having the form 1 over a, where a is a positive integer. The conjecture can be stated as follows. For every integer n greater than 1, the fraction 4 over n can be written as the sum of three distinct unit fractions, i.e., 4 over n equals 1 over x plus 1 over y plus 1 over z, where x, y, and z are positive integers. The goal of the conjecture is to determine whether for every integer n greater than 1, it is possible to find positive integers x, y, and z such that the equation holds. A unit fraction is a fraction where the numerator is 1, so the equation involves expressing 4 over n as the sum of three unit fractions. For example, for n equals 2, we have 4 over 2 equals 2, and we can express this as 2 equals 1 over 2 plus 1 over 3 plus 1 over 6. Here, x equals 2, y equals 3, and z equals 6, and the equation holds. The Erdős-Strauss conjecture suggests that such a representation exists for every integer n greater than 1. Despite many attempts and partial results, the conjecture remains unproven. For example, for n equals 3, we have 4 over 3 equals 1.3333. A valid representation is 4 over 3 equals 1 over 2 plus 1 over 3 plus 1 over 6. For n equals 6, we have 4 over 6 equals 2 over 3, and we can express this as 2 over 3 equals 1 over 2 plus 1 over 3 plus 1 over 6. The Erdős-Strauss conjecture is a particular case of a more general class of problems in Diophantine equations, which involve finding integer solutions to equations involving only integers. In this case, it is a problem about finding integer solutions to the equation 4 over n equals 1 over x plus 1 over y plus 1 over z. The conjecture is of great interest because it connects number theory, particularly the study of fractions, with the properties of integers and their divisibility. Although no general proof has been found, the conjecture has been checked for many values of n, and for all tested cases, a solution exists. Despite the fact that the conjecture remains unsolved for general n, mathematicians have made partial progress in understanding the problem. It has been shown that solutions to the Erdős-Strauss conjecture exist for many values of n, and techniques from continued fractions, greedy algorithms, and modular arithmetic have been applied in attempts to find a general solution. In particular, partial results show that for many values of n, the conjecture holds, and researchers have used computational methods to test it for very large values of n. As of today, however, there is still no known proof for all integers. The Erdős-Strauss conjecture is important because it is a simple yet deep question in number theory. Its solution would provide insight into the behavior of fractions and Diophantine equations, as well as add to the understanding of how integers relate to each other in additive ways. The conjecture has attracted the interest of mathematicians and number theorists for decades. In conclusion, the Erdős-Strauss conjecture remains an open problem in number theory, posing the question of whether 4 over n can always be written as the sum of 3 distinct unit fractions for every integer greater than 1. Although it has been tested extensively and holds for many values of n, a general proof has yet to be found, making it one of the many unsolved problems in mathematics. Littlewood's conjecture is a long-standing unsolved problem in analytic number theory, proposed by the British mathematician John Littlewood in the early 20th century. The conjecture deals with the distribution of prime numbers and how their reciprocals behave under specific conditions. The conjecture can be explained in the following way. Littlewood's conjecture suggests that for any real number x, the sum of the reciprocals of prime numbers raised to a given power, greater than 1, will eventually be arbitrarily close to 1 as more and more terms are considered. In other words, when we sum the reciprocals of primes raised to some power, this sum will approach a limit, and that limit will be 1. To understand this conjecture more clearly, we must first define a few key terms. Prime numbers. These are natural numbers greater than 1 that have no positive divisors other than 1 and themselves, e.g., 2, 3, 5, 7, 11, etc. Reciprocal of a prime. The reciprocal of a prime number p is simply 1 over p. For example, the reciprocal of 2 is 1 over 2, the reciprocal of 3 is 1 over 3, and so on. Zeta function. The Riemann zeta function is a fundamental function in number theory that involves the sum of reciprocals of powers of integers. It is typically written as a summation running over all natural numbers n, where n is raised to some complex power. Littlewood's conjecture is often related to this function in the context of prime number reciprocals. The conjecture suggests that as the sum of the reciprocals of prime numbers raised to some power grows, it will eventually get arbitrarily close to 1, no matter how large the numbers are. For example, consider the sum s + 1 over p1 plus 1 over p2 plus 1 over p3 plus, where p1, p2, p3, and so on are the prime numbers. As more primes are added, this sum will tend to approach 1. This conjecture has deep connections to the distribution of primes, which is a central theme in number theory. The prime number theorem, for example, describes the asymptotic distribution of prime numbers among the integers. The conjecture also relates to the study of Dirichlet L functions, which are important in understanding the distribution of primes in arithmetic progressions. Although the conjecture has been tested numerically for many cases, no proof has been found, and the behavior of these sums for large values of x remains unclear. The question is whether these sums approach 1 in all cases, or if there are exceptions that prevent this from happening. This challenge makes the conjecture a part of the broader study of prime number theory, where mathematicians are always seeking to understand the deeper patterns and properties of primes. One of the difficulties in proving Littlewood's conjecture is the complex nature of prime numbers and their irregular distribution. While primes become less frequent as numbers get larger, they still exhibit a certain level of unpredictability. This makes it challenging to determine the exact behavior of the sums of their reciprocals. In conclusion, Littlewood's conjecture is a deep problem in analytic number theory that continues to fascinate mathematicians. It suggests that the sum of the reciprocals of prime numbers raised to a certain power will eventually approach 1. Despite being unproven, the conjecture has provided valuable insights into the study of prime number distribution and has motivated further research in the field of number theory. If proven, it would offer a significant contribution to understanding the distribution of primes and their properties in the context of summing their reciprocals. Shanuel's conjecture is a famous unsolved problem in transcendental number theory, proposed by the mathematician Stephen Shanuel in 1969. It deals with the algebraic independence of certain numbers related to the exponential function and its properties. The conjecture is central to understanding the deep connections between algebraic numbers, those that are solutions to polynomial equations with integer coefficients, and transcendental numbers, those that are not solutions to any such polynomial equations. Shanuel's conjecture is often stated in terms of complex numbers and involves the transcendence of certain numbers involving the base of the natural logarithm and pi, two of the most well-known transcendental numbers. The conjecture can be summarized as follows. If a set of complex numbers x1, x2, xn are linearly independent over the rational numbers, then the numbers e raised to the power of x1, e raised to the power of x2, e raised to the power of xn are algebraically independent over the field of rational numbers. In simpler terms, Shanuel's conjecture asserts that if you take a set of complex numbers that are not related by any simple rational relationship, they are linearly independent, then the exponentials of these numbers will also not satisfy any polynomial equation with rational coefficients. For example, consider a simple case where you have a set of two numbers, x1 and x2, where these numbers are linearly independent over the rationales. According to Shanuel's conjecture, the numbers e raised to the power of x1 and e raised to the power of x2 should be algebraically independent, meaning there is no polynomial with rational coefficients that can relate them in any way. This is an incredibly strong statement, as it provides a way to understand the relationship between these transcendental numbers. The conjecture, if proven, would have profound implications for the study of transcendental numbers and algebraic independence. It would give mathematicians a more concrete understanding of the behavior of transcendental numbers like e and pi when combined in exponential forms. It also has connections to transcendence theory and other areas of mathematics, such as Diophantine approximation, which studies how closely algebraic numbers can approximate real numbers. Shanuel's conjecture implies some well-known results, such as the Lindemann-Weierstrass theorem, which shows that pi is transcendental, as it is impossible for e raised to the power of I pi to be algebraic. The Lindemann-Weierstrass theorem can be seen as a specific case of Shanuel's conjecture, when considering I pi and 1 as linearly independent numbers. Despite its apparent simplicity, Shanuel's conjecture remains unproven, and it has eluded mathematicians for decades. It is widely considered one of the most important open problems in transcendental number theory. Several partial results have been obtained that support the conjecture, but a general proof for all cases has not yet been discovered. One of the reasons Shanuel's conjecture is so significant is that it provides a deeper understanding of the structure of transcendental numbers. If proven, it would shed light on the complex relationships between algebraic and transcendental numbers and their interactions in various mathematical settings. In conclusion, Shanuel's conjecture is a key unsolved problem in transcendental number theory. It posits that the exponentials of linearly independent complex numbers are algebraically independent. Although no general proof has been found, the conjecture has profound implications for number theory and related fields. It remains an open problem of great importance, and its solution would represent a major breakthrough in our understanding of transcendence and algebraic independence. Polignac's conjecture is a famous unsolved problem in number theory that deals with the distribution of prime numbers. It was proposed by the French mathematician Alfred Polignac in the 19th century and is sometimes referred to as Polignac's hypothesis. The conjecture concerns the occurrence of prime gaps, which are the differences between consecutive prime numbers. In its simplest form, Polignac's conjecture states that for any positive even integer k, there are infinitely many pairs of consecutive prime numbers that differ by exactly k. In other words, there are infinitely many prime numbers p and q such that the difference between p and q is k, where k is an even integer. The conjecture suggests that these prime pairs are not just a finite occurrence, but will continue to appear infinitely often as prime numbers become larger. To understand the conjecture better, let's consider a few examples of small even integers k and the gaps between consecutive primes. For k ℏ 2, the conjecture asserts that there are infinitely many pairs of primes that differ by 2. These pairs are known as twin primes. Examples include the pairs 3, 5, 5, 7, 11, 13, 17, 19, and so on. Although many twin primes have been found, no one has proven that there are infinitely many such pairs. For k equals 4, Polignac's conjecture asserts that there are infinitely many pairs of primes that differ by 4. Examples include the pairs 3, 7, 7, 11, 11, 13, 17, and so on. For other even values of k, the conjecture asserts that there are infinitely many prime pairs that differ by k. The conjecture is a generalization of the twin prime conjecture, which specifically concerns the case where k equals 2. Polignac's conjecture is closely related to the twin prime conjecture, which posits that there are infinitely many pairs of primes that differ by 2. However, Polignac's conjecture extends this idea to include any even integer k, not just 2. In other words, it suggests that prime gaps of all even sizes occur infinitely often. The conjecture is still unproven, and proving it remains one of the major unsolved problems in number theory. Despite this, significant progress has been made in understanding prime gaps, and various results have been obtained that support the conjecture. For example, the prime number theorem provides an understanding of how primes are distributed, and recent advances in analytic number theory have led to improvements in the bounds on prime gaps. One of the major difficulties in proving Polignac's conjecture is that the distribution of prime numbers is not fully understood. While there are many patterns and properties of primes that have been discovered, primes are still somewhat unpredictable, and understanding how they are spaced apart, especially as they grow larger, is a challenging task. If Polignac's conjecture is proven, it would have profound implications for number theory, particularly in the study of prime numbers. It would provide new insights into the distribution of primes and their behavior in relation to gaps. The conjecture also has connections to other important conjectures and theorems in number theory, such as the Goldbach Conjecture and the Riemann Hypothesis, as these also concern the distribution and properties of prime numbers. In conclusion, Polignac's conjecture is an important open problem in number theory that generalizes the idea of twin primes to include all even gaps between consecutive primes. While it remains unproven, the conjecture has deep connections to the study of prime number distribution, and its resolution would mark a significant breakthrough in the understanding of prime numbers. The Monty Hall problem is a famous puzzle in mathematical probability based on a game show scenario. It was named after Monty Hall, the host of the American television game show, Let's Make a Deal. The problem is a classic example of how probability theory can lead to counterintuitive results. The setup of the problem is as follows. A contestant is presented with 3 closed doors. Behind one of the doors is a prize, often a car, and behind the other 2 doors are goats, or non-prizes. The contestant initially selects one of the doors, but the door is not opened right away. Instead, the host, Monty Hall, who knows what is behind each door, opens one of the other 2 doors to reveal a goat. Monty then gives the contestant the option to either stick with their original choice or switch to the other unopened door. The question is, what should the contestant do to maximize their chances of winning the prize? Stick with their original choice or switch to the other door? At first glance, many people might think that once Monty reveals a goat behind one of the doors, the contestant has a 50-50 chance of winning, as there are 2 remaining doors. However, probability theory tells us that the best strategy is actually to always switch doors, as this increases the contestant's chances of winning to 2/3. Here's a breakdown of why switching is the better option. Initial choice. When the contestant first chooses a door, there is a 1 in 3 chance, approximately 33.33%, that they have chosen the door with the prize, and a 2 in 3 chance, approximately 66.66%, that they have not chosen the door with the prize, 66.67% that they have chosen a door with a goat. Monty's action. After the contestant makes their initial choice, Monty opens one of the remaining doors to reveal a goat. Importantly, Monty always knows where the prize is and will never reveal the prize behind the door. This action gives additional information to the contestant. If the contestant initially picked a goat, which with probability 2 in 3 is likely, then Monty will be forced to open the other door with a goat, leaving the only remaining unopened door with the prize. Switching. If the contestant switches after Monty reveals a goat, they win if they initially chose a goat, which has a probability of 2 in 3. If the contestant sticks with their original choice, they win only if they initially chose the prize, which has a probability of 1 in 3. Therefore, switching gives the contestant a 2 in 3 chance of winning 3 chance of winning, whereas staying with the original choice gives them only a 1 in 3 chance. To understand the probabilities more clearly, imagine a simulation where the contestant plays the game many times. If they always switch, they will win approximately 2/3 of the time. If they always stay with their initial choice, they will win only 1/3 of the time. This counterintuitive result arises because the contestant's initial choice has a higher likelihood of being wrong, since there is a 2 in 3 chance of selecting a goat, and Monty's action of revealing a goat provides additional information that increases the probability of winning by switching. The Monty Hall problem demonstrates an important principle in probability, that additional information, in this case Monty revealing a goat, can dramatically change the odds of an event. By always switching doors, the contestant increases their chances of winning from 1 in 3 to 2 in 3, making switching the optimal strategy. This problem has been the subject of much debate and has puzzled people for years, but mathematically the optimal strategy is clear. Switching is the best choice. Hilbert's 16th problem is one of the 23 famous mathematical problems proposed by David Hilbert in 1900. This problem deals with the topology of algebraic curves and surfaces, specifically focusing on the behavior of real algebraic curves and their arrangement in the plane. It remains one of the most challenging problems in algebraic geometry and topology. At its core, the problem is divided into 2 main parts. The first part concerns the topology of real algebraic curves, particularly the possible configurations of their connected components in the real plane. The second part extends this question to real algebraic surfaces and the arrangement of ovals that these surfaces can form. The problem essentially seeks to classify and understand the number, shape, and relative positioning of these components. Real algebraic curves are defined as the set of real points that satisfy a given polynomial equation in two variables. These curves can have complex and intricate structures, forming loops and separate regions in the plane. The study of these structures is deeply connected to the broader field of topology, which examines the properties of shapes that remain unchanged under continuous transformations. One of the key challenges in this problem is determining the maximum number of connected components that a real algebraic curve of a given degree can have. Hilbert himself made significant progress in this area by establishing upper bounds on the number of such components. However, the precise classification of all possible configurations remains unresolved for higher degree curves. In addition to curves, the problem also extends to real algebraic surfaces, which are defined by polynomial equations in three variables. These surfaces can have even more intricate topological features, such as nested ovals and intersecting regions. Understanding these structures requires advanced mathematical tools, including algebraic geometry, differential topology, and singularity theory. One of the most famous contributions to this problem was made by the Russian mathematician Vladimir Arnold. His work in the 20th century provided new insights into the structure of real algebraic curves and their critical points. Arnold's contributions helped establish connections between Hilbert's 16th problem and dynamical systems, illustrating how polynomial equations can describe complex real-world phenomena. Despite these advances, many aspects of the problem remain open. The classification of all possible topological arrangements of real algebraic curves is still incomplete, particularly for equations of high degree. Mathematicians continue to explore new techniques, including computational methods and numerical simulations, to gain deeper insights into this long-standing question. The significance of Hilbert's 16th problem lies not only in its difficulty, but also in its fundamental role in shaping modern algebraic geometry. It highlights the deep interplay between algebra and topology, demonstrating how polynomial equations can encode intricate geometric and topological properties. As research in this area progresses, mathematicians hope to uncover new structures and develop more refined classifications, bringing us closer to a full understanding of the problem. Singmaster's conjecture is a well-known unsolved problem in number theory that concerns the frequency of integers appearing in Pascal's triangle. Proposed by David Singmaster in the 1970s, the conjecture suggests that there exists a universal upper bound on how many times any given integer can appear in Pascal's triangle, aside from the number 1, which appears infinitely often. Pascal's triangle is a triangular arrangement of binomial coefficients, where each entry represents the number of ways to choose a subset of elements from a larger set. The first row starts with a single 1, and each subsequent row is constructed by summing adjacent entries from the previous row. This simple rule produces a triangular array filled with integers, many of which appear multiple times. The key question in Singmaster's conjecture is whether there exists a maximum number of times a non-trivial integer can occur in Pascal's triangle. While the number 1 appears infinitely often, all other numbers seem to have a limited frequency. For example, the number 6 appears 4 times in the triangle, while the number 10 appears 5 times. However, no number has been found that appears more than a certain number of times, leading to the conjecture that there is a finite upper bound. Singmaster originally proved that any integer in Pascal's triangle appears at most a logarithmic number of times in relation to its value. Subsequent research has improved upon this result, narrowing down the possible upper limits. Some mathematicians have conjectured that the true bound may be small, possibly as low as 8, though this remains unproven. One of the challenges in proving or disproving Singmaster's conjecture lies in understanding the distribution of binomial coefficients. These coefficients satisfy complex arithmetic properties and are deeply connected to the study of prime numbers and divisibility. Since the values in Pascal's triangle grow exponentially, identifying patterns in their repetitions requires advanced combinatorial and number-theoretic techniques. Several approaches have been used to explore the conjecture, including computational methods that search for repeated values in Pascal's triangle. So far, all known numbers that appear multiple times fit within the expected bounds, but no general proof has been found to establish a strict limit. The problem remains an intriguing mix of combinatorics, algebra, and computational mathematics. Singmaster's conjecture has broader implications beyond its specific question. It relates to the behavior of binomial coefficients, which are fundamental in probability theory, combinatorial identities, and even cryptographic algorithms. A deeper understanding of this problem could shed light on other open questions in discrete mathematics. Despite decades of research, Singmaster's conjecture remains unresolved. Mathematicians continue to refine estimates and search for new theoretical breakthroughs that might lead to a conclusive answer. Whether the conjecture is ultimately proven or refuted, it highlights the richness of Pascal's triangle and the hidden complexities within seemingly simple mathematical structures. The Frobenius coin problem is a classic problem in number theory that belongs to the field of Diophantine equations. It concerns the largest monetary value that cannot be obtained using only coins of specified denominations. This problem is particularly relevant in combinatorics and has applications in algebra, optimization, and even economics. The problem is named after the German mathematician Ferdinand Frobenius, though its origins trace back to earlier studies of integer solutions to linear equations. The fundamental question it asks is, given two or more coin denominations that are relatively prime, what is the largest amount of money that cannot be formed using only these denominations? For the case of two coin denominations, an elegant formula provides the answer. If the denominations are chosen as two relatively prime positive integers, the largest value that cannot be obtained using any non-negative integer combination of these denominations is given by a simple arithmetic formula. However, when more than two denominations are involved, no general formula exists, and the problem becomes significantly more difficult. This problem is an example of a linear Diophantine equation, which seeks integer solutions to equations of the form involving sums and multiples of integers. Finding the largest unattainable value requires an understanding of modular arithmetic and number-theoretic properties. In addition to its theoretical importance, the Frobenius coin problem has practical applications in economics and operations research. It helps in designing efficient currency systems, understanding pricing structures, and optimizing resource allocation problems. The problem also arises in computational mathematics, where algorithms are developed to compute solutions for larger sets of coin denominations. Despite its apparent simplicity, the problem remains challenging when extended to three or more coin denominations. Various bounds and approximations have been proposed, but a complete closed-form solution for arbitrary sets of numbers is still unknown. Researchers continue to explore new mathematical techniques and computational methods to analyze this problem further. The study of the Frobenius coin problem illustrates the beauty of number theory, where simple questions about integers lead to deep and complex mathematical challenges. It also highlights the interplay between pure and applied mathematics, demonstrating how abstract mathematical concepts can have real-world implications. Jacobsthal's function. Problem is a question in number theory related to the behavior of integers in modular arithmetic. It concerns the smallest integer that must be tested to guarantee finding a complete residue system modulo a given integer. This function has applications in number theory, combinatorics, and computational mathematics. The function, often denoted in mathematical notation, measures how far one must search among integers to ensure that a complete set of representatives appears for a given modulus. A complete residue system consists of integers that represent all possible remainders when divided by a modulus. Finding the smallest number that guarantees the presence of all residues is the core challenge of the problem. This function is particularly interesting when applied to prime numbers and their powers. For small values, determining the result is straightforward, but as the modulus grows, the complexity of calculating the function increases. The problem connects deeply with other areas of number theory, such as the study of gaps between integers in modular settings and distribution properties of sequences. One of the key aspects of this problem is its relation to worst-case scenarios in modular arithmetic. It provides an upper bound on how far one must search to ensure that all modular classes appear at least once. This has implications for computational number theory, particularly in algorithm design, where understanding residue systems is crucial for efficiency. Jacobsthal's function problem has been studied extensively, with various upper and lower bounds established. The problem remains relevant for understanding modular properties in a broader mathematical context. It serves as an example of how simple numerical properties can lead to deep and intricate questions in number theory. While primarily theoretical, the function has applications in coding theory, cryptography, and random number generation, where modular arithmetic plays a fundamental role. The study of this problem continues to evolve as mathematicians refine estimates and develop new methods to analyze residue systems effectively. The Borel conjecture is a statement in set theory and topology concerning the structure of certain subsets of the real number line. It asserts that every strong measure zero set is countable, meaning that no uncountable subset of real numbers can have the strong measure zero property. This conjecture has deep implications in the study of measure theory, topology, and the foundations of real analysis. A strong measure zero set is a set of real numbers that can be covered by intervals of arbitrarily small total length. More formally, for any given sequence of positive numbers, however small, there exists a sequence of intervals whose lengths match those numbers and still cover the entire set. Intuitively, such sets should be small in a strong sense, which is why the conjecture suggests that only countable sets can possess this property. The problem was first posed by Émile Borel, a pioneering mathematician in measure theory, who conjectured that uncountable strong measure zero sets do not exist. If true, this would mean that every uncountable subset of real numbers is large in a fundamental way and cannot be squeezed into arbitrarily small coverings. However, proving or disproving this statement requires advanced techniques from set theory, particularly those involving the axiom of choice and infinite combinatorial arguments. One of the most significant developments related to the conjecture is its connection to the Continuum Hypothesis and other independence results in set theory. It has been shown that the truth of the Borel conjecture depends on which axioms of set theory are assumed. Under the standard Zermelo-Fraenkel set theory with the axiom of choice, the conjecture is neither provably true nor false. This means that different models of set theory can yield different answers regarding the validity of the conjecture. Despite its abstract nature, the conjecture has applications in topology, particularly in the study of metric spaces and covering properties. It also has implications in real analysis, where understanding the behavior of small sets is essential in measure theory. Mathematicians continue to explore the problem using techniques from descriptive set theory and large cardinal axioms, hoping to uncover deeper insights into the structure of the real number line. The Borel conjecture remains a central question in mathematical logic and topology. illustrating the complexities of infinite sets and their properties. Its study highlights the interplay between measure, topology, and foundational set theory, making it an important topic for researchers in these fields. Kaplansky's conjecture is a set of open problems in ring theory and algebra proposed by the mathematician Irving Kaplansky. These conjectures primarily concern the structure of algebraic objects such as group rings, division rings, and projective modules. They remain significant in modern algebra, influencing research in non-commutative algebra, module theory, and algebraic K-theory. One of the most well-known versions of Kaplansky's conjecture deals with group rings. A group ring is an algebraic structure formed by combining a group and a ring, allowing the study of both group-theoretic and ring-theoretic properties simultaneously. Kaplansky proposed that if a group is torsion-free, then its group ring over a field has no non-trivial units of finite order. In other words, every unit in the group ring should either have infinite order or be the trivial unit. This conjecture, if true, would impose strong restrictions on the algebraic structure of group rings and provide deep insights into the interaction between groups and rings. Another version of the conjecture concerns idempotence in group rings. An idempotent is an element that, when multiplied by itself, remains unchanged. Kaplansky's idempotent conjecture states that if a group is torsion-free, then its group ring over a field does not contain any non-trivial idempotent elements. This conjecture is significant because idempotents determine how the ring can be decomposed into simpler components. The absence of non-trivial idempotents would indicate that the group ring has a more rigid and indecomposable structure, making it easier to study. Kaplansky also formulated conjectures about division rings, which are algebraic structures where every non-zero element has a multiplicative inverse. One of his conjectures states that every division ring with a finitely generated multiplicative group must be commutative. In simpler terms, this means that if the multiplicative structure of the division ring is generated by a finite set of elements, then the ring must behave like a standard field, where multiplication is always commutative. This conjecture links the algebraic properties of rings with their underlying arithmetic and has implications in the broader study of algebraic structures. These conjectures are particularly challenging because they lie at the intersection of algebra, topology, and number theory. Understanding group rings requires knowledge from various areas of mathematics, including homological algebra, algebraic geometry, and representation theory. Over the years, progress has been made on some special cases, with certain versions of the conjectures proven under additional assumptions. However, the full generality of these statements remains unresolved. Kaplansky's conjectures have applications beyond pure mathematics. They are relevant in coding theory, cryptography, and mathematical physics, where the structure of rings and groups plays a crucial role in constructing models and solving equations. The study of these conjectures continues to be an active area of research, with mathematicians developing new tools and techniques to address the problem. Despite decades of study, Kaplansky's conjectures remain open in their most general forms. Mathematicians continue to investigate these problems, refining related algebraic structures and seeking deeper insights into the nature of non-commutative rings. The conjectures highlight the richness of ring theory and demonstrate how fundamental questions about algebraic operations can lead to profound discoveries across different areas of mathematics.